Hi everyone, we will start in a couple minutes.
Hi Eduard, how are you doing? This is Davide Scaramuzza speaking.
Hi Davide. 1 second, I had to mute my YouTube live stream. I was getting everything in double.
Sure.
Is the sound okay now?
Yeah, choppy.
Choppy? Let me turn it up and on. One, two, three. Is it better?
Your microphone is now connected to another thing. I love it that our YouTube streams are always starting with technical difficulties in audio or video.
Does it work now? Does it work? Does it not work?
I think your microphone is now your desktop's microphone or something, not the one in the headphone.
That is, I don't know.
It's okay. We just hear your laptop burning a little bit. It's fine. Not the end of the world.
It's not great. I don't know how to switch it. I'm using the web interface. I cannot install Zoom.
Oh.
Not on this laptop. Wait, microphone. It says, I don't know. It says that it's on using my headphones. It's not using my.
Okay.
The sound is just not very good, I guess.
Yeah, it's a.
Well, I think let's hope that it's not too bad. It's time already. So hi everyone, and welcome to the third edition of the image matching local features and beyond CVPR workshop. The second one that is virtual, and hopefully the last one, now that things are getting a little bit better. There was a bit of a mishap, and the workshop, the CVPR website said that we were supposed to start 2 hours ago, which we obviously didn't do. Hopefully we didn't lose too many of you, and apologize for the inconvenience. I am Eduard, and the workshop is co-organized by my colleagues Vassileios, Judy, Dmytro, Johannes, and Kwang. Let's look at the schedule briefly. So we are in a quick 15-minute welcome session that I'll present. After that, we will have 2 long invited talks from Professors Davide Scaramuzza and Marc Pollefeys. A bit Zurich-centric, but what can you do? I'm also in Zurich. Then we'll have 2 short talks for the 2 papers that were accepted to the workshop. And then we'll have talk about the challenge, the new data sets that we have, the results, and an open discussion session. We have not tried this before, so let's see how it works out. Hopefully we have some participation from the audience. And finally, we'll have 6 10-minute talks from mostly participants to the different challenges, and closing session at the end. The workshop takes place on Zoom, and also it's live on YouTube. So choose whatever you prefer. If you want to use Zoom, the link is available on the CVPR website. Drop questions whenever you have them on chat, and we will try to pass them on to the speakers. If you want to ask questions directly, you can also do that on Zoom, but please wait until the end of the presentation so as to keep things running in some orderly fashion. Okay, so let's talk a little bit about the workshop, because it's the 3rd year that we do this, but some attendees are probably new. The focal point is matching, image matching, mostly of rigid structures, think building facades. So it's mostly, we are all working on 3D reconstruction, problems such as stereo or extraction from motion. And we are interested in dealing with these problems across all the kinds of transformations that you can imagine, such as white baselines, differences in time, in weather, in illumination, occlusions, etc. And the link in common with these problems is the local features part in the title of the workshop, because local features were at some point the state of the art on a wide array of computer vision problems, but that is not the case now that we have shifted to deep learning. But for 3D reconstruction, we still use, arguably, you can debate this, but we still use mostly local features. They are still the state of the art. And beyond, that's also in the title of the workshop, because we know that that will probably not always be the case, and we want to keep an eye on it and see how the field evolves. One of the reasons that we started this workshop, particularly in my case, is because of the problems in evaluating this type of algorithms, local features and local feature matchers. New papers come out all the time, many of them by us, the organizers of this workshop, but it can be difficult to know what actually works, because the benchmarks that we have are often saturated. They use metrics which you may argue are not necessarily what you should measure. They have biases in the data, or simple problems such as they are decentralized and you don't even know, what papers to look at to compare all of the results on one data set. Let's look at some of the data sets that people have used historically for this problem. The first one, I would say, was Matthew Brown's dataset, which was patch-based, had 3 sequences. And briefly looking at some results, what's interesting is that, as you see, it saturated very quickly, and up to a point where in 2019, the metric started going up. Here, obviously, lower is better. And it's mostly fallen out of favor. So people don't really develop patch-based descriptors as much as we used to. But the interesting part in here is not the end of the bottom of the plot, but the difference between the top of the plot and the bottom. So this tells you that SIFT, which is a seminal work in computer vision local features, is much, much, much worse than these modern papers. Is this true? Probably not. This is something that we saw when I was working along with Kwang on Lift, which was kind of a learned version of SIFT, where we tried to learn both the key point detector, the orientation detector, and the descriptor all at the same time. So we got the paper published because we got nice results, as you see in here. But one thing that we found was that on some data sets, the left, middle, and right plots are from different data sets. On some datasets, SIFT seemed to work not only as well as many of the methods developed between SIFT and Lift, but even better. And how is that possible? How does that mix with the slide which we just saw, which seems to say the exact opposite, right? There are other datasets that people use to evaluate local features. One is HPatches, that was developed by Vassileios, another organizer of the workshop, still very much in use. It's a good data set, but it has limitations. One very strong limitation is that it only has perspective and illumination changes. So the ground truth is a homography, and the scenes are just basically a plane. And it originally was devised to be used to evaluate patch descriptors. People have also used the homographies to measure different things, but it was focused on intermediate metrics. And another data set that people use, also co-developed by a co-organizer of the workshop, Johannes, was based on Colmap, a work of his that is still today one of the best frameworks to do structured from motion reconstruction. And it's nice because it's very large scale. You are actually trying to do reconstructions of entire cities or close to it. But it has the problem that at that scale, you just don't have any ground truth. So it relies on intermediate metrics, such as how many images can you register, how many points are in your 3D models, how low is the reprojection error. But that is not necessarily what you want to measure, right? And that is something that you cannot do because you don't have ground truth, right? Capturing ground truth at a large scale is basically impossible. This is something that some papers have tried to do, such as Stretch's paper in 2008 with this sequence that you have probably seen, which has very nice, very dense ground truth, such as the depth maps that you see on the left. but it has only 2-3 scenes and just dozens of images, right? So it's obviously limited. So our solution was, okay, let's try to create a challenge with data that we were working with at the time, and try to make it public, and try to have a workshop that is centered on the challenge. We still have invited talks from top-level professors and researchers, but we are going to put strong focus on the challenge. We kept working on it. The idea was we wanted to figure out how to properly evaluate these algorithms, and we published a paper on it. So if you are curious, there is an IJCV paper that we published last year. We'll talk a little bit about that at 11:15. And we want to focus on the meeting between theory, new papers that try to do cutting-edge research, and practice with these large-scale data sets. And the workshop ideally would be a meeting point for the people who work on these problems, who develop these new algorithms and publish these papers, where we all try to figure out what is actually the state of the art on this problem. We started the 2019 workshop with this slide, which was kind of trying to illustrate this point where we are one of the last bastions of classical computer vision in a way, because we are still using geometry, but we are surrounded by deep learning. So in 2020, this was the slide that we used was a bit closer, and in 2021, where are we? So one could argue that the battle has been lost. Not exactly, but yeah, we are going in that direction. Let's recap a little bit. So in 2019, we held the first version of the workshop and the challenge. We had the image matching challenge and also a Silva challenge organized by Vassileios back at Scape. Scape has now been acquired by Facebook. And the winners were using mostly learned patch descriptors, things like contact desk or hardnet that take patches as input, typically on safety points, and produce learned descriptors, and context networks for matching. In 2020, the challenge grew a lot because we open sourced the code base for the benchmark, and people could do proper validation. And it was nice to see that many of the top performers were actually like groundbreaking papers, like Superglue, that won many competitions last year, RLAM or Disk, for instance. These were 3 of the 4 prizes that we awarded last year in the image matching challenge. In 2021, we'll talk about that later in more detail, but we have 2 new data sets on the image matching challenge and a new challenge organized by Vassileios, which is a synthetic data set called SimLocMatch. And we have observed, again, we'll discuss that a bit more later, but we have observed that the best performers have shifted more to engineering, trying to figure out what actually works and does not with some of these technologies. Some of them use papers such as Superglue or Disk, but build on top of that and try to do more incremental improvements, which I guess is to be expected. And question is now, what do we do for next year? We'll have an open discussion session later, as I said. And if you have ideas on how we can do this better, what do we need to do to remain relevant or increase the relevance of the challenge, please let us know. I would like to mention, though, that there are also many papers introduced recently that just try to do this shift from local features to something else that I was mentioning about, the beyond. We have 3 of them, 2 are CVPR 2021 papers, and 1 was recently submitted to a different conference. And we have talks for all of them at the end of this workshop. They are LOFTR, a detector-free local feature matching with transformers by Jiaming Sung et al. COTR, correspondence transformer for matching across images. These 2 papers are detector-free, or can be detector-free, in the sense that you just give it a point in one image and another image, and you'll be given the correspondence in return. And they use transformers, which are really powerful tools, as we know now in computer vision. And the last one is learning accurate tense correspondences and when to trust them, another CVPR 2021 paper by Kwang, which actually goes in a different direction and just tries to do tense reconstruction. So that's it for the introduction. I'll now move to the two embedded talks. So now Davide Scaramuzza will join us. He's a professor who holds a joint position at the University of Zurich and ETH Zurich, where he is the head of robotics, the robotics and perception group. His research lies on the intersection of a bunch of different fields, including robotics and SLAM, especially with flight-based robots, that is with drones, and computer vision. And lately with cutting-edge devices such as event cameras. He'll be sharing some of that research with us today, and I'm quite excited about it. So Davide, if you are ready, can take the screen over.
Yes, thanks a lot, Eduard, for the introduction and for the invitation. I'm ready. You need to enable me to share the screen. Okay.
I think I did.
Yes,
Edward...
yes, you just did. Yeah, indeed.
Yeah.
Now it works. Okay. Okay, you should be able to see my slides.
Yep.
So basically, I decided to talk about event cameras and, of course, within the context covered by the workshop. So for image matching and structure from motion. But we'll also show some of these applications to drones because image matching, especially feature matching, is super important for reliably flying, so preventing drones from crashing away. So let me start. So what are event cameras and why do we need event cameras first? So we are all experts in computer vision. And as you know, we have been using cameras, frame-based cameras for about 60 years. However, they are not good enough for some applications, as you can see in these two images. First of all, standard cameras suffer from high latencies. That is actually related to the motion blur. That actually causes motion blur. And this is actually due to the fact that when we take images, we need to expose the pixels for a certain amount of time, called exposure time. And it turns out that, of course, when you are in a bright light, like in a bright day, then the exposure time is about 1 millisecond. But when you move to indoor environments or even in low light environments, then the exposure time is about 100 milliseconds or even longer than that, which causes a lot of motion blur. Not only that, but actually, if you think about many applications that are relevant today, like automotive, or drones, so you want to avoid crashing or colliding against pedestrians and other vehicles. So you want to be able to predict other vehicles and pedestrians' motion as fast as possible. You don't want to wait for the, for the full exposure. Another problem with standard cameras is that they typically suffer from low dynamic range. You see this very well in this picture. So event cameras do not suffer from these problems. What is an event camera? An event camera is a camera that only measures motion in the scene. Look at the top right video in this slide. Here you see what one of the outputs of the event camera actually looks like. So only the pixels that detect motion in the scene will trigger information. Why do we have two colors, red and blue? Because, as you will see in a moment, the pixels of an event camera are independent of one another. And every time that a single pixel detects motion in terms of brightness changes, so that pixel will trigger an event. So the brightness change can be either positive or negative. And that's why you see here two colors, red and blue. So red for positive and blue for negative. However, what you need to understand is that the output of an event camera is not synchronous like standard frames, but rather asynchronous. So every time that a single pixel detects a change of intensity, that pixel will trigger an event. So the output to the stimulus here, you see here I was moving this disk. So the output would be a spiral of events in space and time. So as long as there is motion, there are events. If there is no motion, there are no events. So you have a drastic reduction of bandwidth in case there is no motion. So that's one of the key advantages of event cameras. But now you understand this camera works in differential mode. I will come to that in more detail later. And this differential modality allows four key advantages. First of all, a latency of the resolution of microseconds, no motion blur, ultra low power, because basically you only trigger information when something is moving. So on average, you have a power consumption of 1 milliwatt versus 1 watt of a standard camera. and also a very high dynamic range. Again, this is due to the differential modality of the sensor. But there is a problem. The problem is that because the sensor is asynchronous, you cannot directly apply standard computer vision algorithms, but you can either adapt standard computer vision algorithms or you can develop new ones. Now, what you need to understand very well is the difference with respect to a traditional camera. Here on the top, you see how a traditional camera works. So we get a frame all at the same time at constant time intervals. By contrast, an event camera outputs an asynchronous stream of events at microsecond resolution. And the beauty of the event camera is that the stream of information comes continuously in time. So basically, it allows very low latency applications without the need to wait for the next frame to arrive, neither for an exposure time. And this, as I will show you later, is very important, for example, for some safety critical applications like robotics. Now, what is an event? An event is a data structure that contains three different entities. The first one is a timestamp, a microsecond resolution. Then we have the pixel coordinates. And then we have the event polarity. What is this? This is the sign of the change of intensity. So it's the sign of the derivative of the light intensity over time. So the sign can be either positive or negative. In this case, we will have either +1 or -1. Let's try to see this one more time. So an event camera implements a so-called cross-level sampling. So let's focus now at a single pixel. So let's assume that this is actually the intensity at a single pixel over time. Actually, the event camera measures the logarithm of the intensity, not directly the intensity. So when is an event triggered at this pixel? So let's assume that there was an event triggered at time 0. The next event will be triggered only when the intensity at that pixel passes a threshold. So when the intensity difference between the current time and the previous event passes a threshold, which is usually denoted by C. This is also called the contrast sensitivity. So this is basically now the event generation model, this formula here. Whenever the difference of the logarithm of the intensity at the current time and at the previous event time is equal to a threshold, positive or negative, depending on whether it's a positive or negative direction of intensity, then an event is generated. Now, what are the consequences of this cross-level sampling? You see it here. Now we have a negative event, negative, negative, positive again, positive, 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 negative, negative, and negative again. You see the key distinction of an event camera with respect to a standard camera here. You see that basically the generation of the events is completely asynchronous. And in fact, it's only dictated by basically when this threshold is passed. Now, people always ask me, who sells event cameras? How much are they? So I decided to put this slide for you today. So there are 4 companies, to my knowledge, that currently sell event cameras. There is Prophecy, that is partnering with Sony. There is InSightness, that was bought by Sony. There is a Select Pixel from China that was bought by OmniVision. And there is Innovation from Zurich that is partnering with Samsung. Now, all these camera manufacturers manufacture event cameras very similarly. However, you may have different flavors. For example, Prophecy, InSightness, and Innovation and Select Pixel all provide, in addition to the events, an IMU, so an inertial measurement unit. But for example, the Prophecy and the Innovation sensor provide, for example, also frames in addition to events. So these are pixels that I can both trigger events or intensity. In addition, the Innovation sensor is the only one that can also provide RGB frames and RGB events. And this is actually pretty new. So it's only sold by Innovation. And you see here how it works. They put a Bayer pattern on the top of the CMOS sensor. So basically you get events that react to either red, green, or blue. As simple as that. Now, remember what I told you about the mathematical model of generation of the events. It's this one here. An event is generated whenever the difference of the logarithm of the intensity at the same pixel passes a threshold. Now, for many applications like structure from motion and feature matching and tracking, it is actually more convenient to use a first-order approximation of this generative event model. So let's call log I just I. And let's consider basically the pixel P, which is the projection of a very simple structure, a black to white transition. It's a very simple toy example. And this is what the camera would actually see, a standard camera would actually see. Now, the generative event model is this one over here. An event is generated, this is of course just a first order approximation, but an event is generated whenever the dot product between the gradient at the pixel location of the observed patch times the optical flow vector is basically equal to this threshold. I save you the derivation, but I give you the intuitive proof. The intuitive proof comes from the fact that if you move an event camera parallel to an edge, you will see no events. You will see events if you move the event camera in any other direction. And you will have a maximum generation of the events if you move in the perpendicular direction to the edge. And so I prove you that this is basically a scalar product. Now remember, though, that an event camera doesn't give you the gradient of the patch and neither the optical flow. It only gives you the event rate. So at a single pixel, you can only measure basically how many events per second are going to be generated. However, you understand that this formula is very precious because it allows us to apply the famous Bayesian framework. So you can independently or alternatively estimate the gradient and the optical flow and therefore do SLAM. So let me show you some applications of this. So we gave one of the first applications for 6DoF camera tracking from a photometric depth map. So what is a photometric depth map? Assume that you have a point cloud where each point is not just X, Y, Z, but also you have the grayscale intensity. What we can do is that we can then use the generative event approximation in order to estimate the motion of the camera with respect to this photometric depth map. Why is this useful? Well, this is actually very useful for virtual reality and augmented reality applications. So if you talk to virtual reality and augmented reality companies, they will tell you that they would like actually to save as much energy as possible. And so any watt or even milliwatts of energy you can save is actually a plus. So event cameras would in principle allow you to use the standard camera at a very low frame rate and instead use the events in between frames to do low energy camera tracking. So that's the whole idea that companies are exploring. We can run this in real time on a smartphone CPU, and let me show you a video here. What you see in blue here is the estimated pose of the camera, and in red, in transparent mode, is actually the ground truth. What we are doing is that we are using basically the Bayesian framework. Now we know the map, so we apply this first order approximation of the generative event model to estimate the motion of the camera with respect to the space. A cool application of this is that not only you have a very low latency, a very low power consumption, but you can also tackle very aggressive motion. For example, when you shake the camera very fast in the scene. And here I'm showing basically an event camera post-tracking compared to frame-based camera tracking. The frame-based camera post-tracking is shown in red, and the event camera post-tracking is shown in blue. As you can see, basically, the standard camera post-tracking fails as soon as you start moving too fast because of motion blur, because you basically lose features. But now I would like to go more in the specifics of feature tracking. And so I would like to talk about what we call event-based KLT tracking. you all know very well KLT is one of the fundamental building blocks of computer vision that is used now in many companies. What we investigated in this IJCV paper, you find below, is an algorithm that allows you to track features asynchronously, independently from one another, using only the events in the blind time between two frames. So a crucial application of this, again, is low latency. And also, it's super robust to HDR and high-speed motions, as I will show you. How does it work? So it's an adaptation of the famous KLT to event cameras. To understand that, consider, for example, the last frame. Let's assume for now that you have a Harris feature that you want to track. So this box basically is a Harris feature that you want to track. So let's assume that now you are starting tracking, okay? So we are at an arbitrary time. And this is now all the events that we generated so far. We focus on a particular space-time volume around the potentially tracked feature. Let's look more closely to this patch, spatiotemporal patch. What you can do, what we do, is that we aggregate the events in this spatiotemporal patch. What does it mean to aggregate the events? It means that we can, at each pixel location, sum up all the positive and negative events. Remember, the positive stands for +1 and negative stands for -1. So if you do this event aggregation, what do you get? You get a grayscale patch. Now, the beauty of this is that in principle, you can do this event by event. But here, for simplicity, for convenience, I'm showing you like at the frame level, okay? But remember, this is actually running continuously, in principle, at the event resolution. Now, this is what the event camera can give you. But now, how do we track features from the last frame within the event stream? Well, now we can apply, basically, the brightness constancy assumption. So let's look at the frame location of the Harris feature. We can predict where the feature will appear using the optical flow equation and the brightness constancy assumption. So this is just the brightness constancy assumption. Using the brightness constancy assumption, we can predict the brightness increment, the same brightness increment that we were measuring from the events. So we can now predict it from frames using this simple formula. So the predicted brightness increment is equal to the gradient of the patch times the optical flow times delta t. Now, what is the problem? We don't know what the optical flow is. Okay. By the way, if you do this, okay, now I hope I convince you. Basically, if you knew the optical flow, by multiplying the gradient times the optical flow, you will basically get the predicted brightness increment. Okay, so we can get in principle this from the frame, assuming that you know the warping of the motion from the previous frame until now and the optical flow. And remember, we don't know these two functions. However, what we do in this work is that we estimate both the warping and the optical flow parameters simultaneously by minimizing the photometric intensity difference between the predicted brightness increment and the measured brightness increment. We can do this in real time. And let me show you some cool results. What you see in this video is how the system reacts to fast motions. So here I'm moving the camera, I'm shaking the camera very fast. And what I'm showing you on the right is our tracked features using our event-based Lucas Canade tracker and how this compares against the standard KLT tracker, which is instead running on standard frames. So it lags behind. That's why you see that basically the Lucas Canade features that are the one in magenta are always behind the EQLT features, the ones from events, that are instead always ahead of time. Because remember, we are able, thanks to the event camera, to update the feature location in the blind time between 2 frames. So I think this is actually, it's very interesting. Let me show you another cool application of this to high dynamic range feature tracking. So this is what, for example, an overexposed frame will look like. And this is what an underexposed frame will look like. Now, sometimes it will be difficult to extract features from these overexposed or underexposed frames. However, we can do something with event cameras to initialize features before tracking. What we can do is that we can reconstruct the frame. So we can run image reconstruction, and then we can extract features. And once we have features, we can track them using our event-based KLT tracker. And now you see what is happening. So we are able to extract and track features in environments that are completely either overexposed or underexposed. Let me show you another extreme situation where we switch to low light. So here I turned off the light in the office, and we show you that when there is light, the standard Lucas Canale tracker works, but when there is no light, it doesn't work at all. But if you use an event camera, thanks to the low light sensitivity of the event camera, we are able still to track features also in low light. So I think these results are actually quite important in the field. An application of this feature tracking, feature extraction and tracking, we did it in the context of SLAM, so simultaneous localization and mapping, where the goal is to simultaneously build a map of the environment and localize the camera within it, also called structure from motion. Now, because we are using an event camera, in order to provoke the community, when we made this algorithm, we actually friendly called it Ultimate SLAM. And Ultimate SLAM basically tries to do several things, not only feature tracking, but also it runs a backend, a visual inertial odometry backend that is also able to estimate and optimize the map in background. In order to showcase the advantages of this Ultimate SLAM compared to standard cameras, we thought of a very difficult experiment. Basically, we attached the event camera on a leash. The leash is actually the USB cable of the camera itself. And then we are spinning the camera very fast, like a cowboy. And you can see that when you spin this camera, the camera very fast, the standard camera is basically saturated and also motion blurred. On the other side, the event camera stream, despite looking different, is still very sharp. So we are able to reliably extract and track features. And this is enough to actually reliably estimating the motion of the camera, the trajectory of the camera. Now, we did this in 2018. So since then, we did quite a lot of progress. What are we doing now? We are using this Ultimate SLAM for robots. I show you some application. This one shows an application of Ultimate SLAM to autonomous drone flight in low light. So let me start. Here we command a quadrotor, a quadcopter, to autonomously follow a circular trajectory. And it's using Ultimate SLAM for pose estimation. Then what we do is that we turned off the light. And as you can see, when we turn off the light, the quadcopter is still able to continuously navigate without crashing. Let me show the video again. Notice what happens at the bottom. Here we have the standard camera frames that become completely dark when I turn off the light, while the events instead are always up, even in low light. So we are able to reliably track features and reliably do visual inertial odometry even in low light, thanks to Ultimate SLAM. Let me show you an even more extreme case. This year at ICRA, we presented a system that uses Ultimate SLAM to prevent a quadrotor from crashing when the quadrotor experiences a rotor failure. What is a rotor failure? So I brought with me today for you a quadrotor. What happens actually more and more often nowadays is that sometimes one propeller stops, so one motor fails. When a motor fails, the quadrotor starts spinning on itself because of the principle of conservation of angular momentum. So it starts spinning like a ballerina on itself. So this means that there is a very high centrifugal motion. People tried to control drones after a motor failure before using GPS. But the problem is that GPS doesn't work indoors or near structures, like near buildings. Also, people try to do this with standard cameras, but the problem is that standard cameras may fail when the motion blur becomes predominant. It turns out that with event camera, we can actually prevent quadcopters from crashing from the sky. So let me show that. So what you're going to see in this video is a quadcopter subjected to a rotor failure using, on the left, a standard camera, and on the right, an event camera. And here you can see the event camera stream, both the features being tracked and the raw camera stream. Here, we show you the illumination, the illuminance in the environment. We are reducing the illumination, and what do you see? What you observe is that when the illumination falls below 50 lux, then the standard camera is not capable anymore to reliably estimate the motion and therefore prevent the quadcopter from crashing. Instead, with the event camera, we can go down to 10 lux, which is quite extreme. Okay, let me move on away from robotics. Let me show you some applications of event cameras now to video stabilization. This is now very important for computational photography applications. Here we are using only the stream of an event camera to stabilize the video. How is this possible? How does it work? So without using inertial sensors, how does it work? So we use an algorithm that we presented at CVPR 2018 called contrast maximization. So what this algorithm does is that it works in a holistic fashion. So it uses all the events. So consider the spatio-temporal volume of the events generated, for example, in the last 3 milliseconds. Do you see anything? Can you recognize some structure? Probably not. It looks like a mess to you. However, what our algorithm does is that it tries to extract structure from the mess by warping the spatio-temporal volume according to the direction of motion of the object that generated these events. This can be done, this warping can be done for pure rotation as well as for homographies. Now, you can actually extend this to solve other problems, like, for example, independent motion segmentation. So what you see here is the spatio-temporal volume of events generated by a car moving in Zurich in an urban canyon. There is a pedestrian, there is a bicyclist, and then there is a building in background. We color the events generated by the three objects with different colors. So we are using this contrast maximization framework to segment out all the objects individually. And now you will understand how it works again. Basically, the contrast maximization framework warps the events according to the direction of motion of the object that generates them. If we do this independently for each object, we can segment the pedestrian, the bicyclist, and the background. The problem is we don't know a priori to which objects the events belong to. So what we also solve in this paper is a simultaneous class association, where we do a probabilistic association of the events to their cluster. However, the only prior knowledge that we need to input is the number of classes. This technique interestingly found a lot of applications also in deep learning, because you can, for example, use this contrast maximization as a loss. And an application of this contrast maximization framework that we made is to have a quad roller, again, to dodge dynamically moving objects. So let me show you this video. Here, my student is launching a ball. He's tossing a ball at the quadcopter. And the quadcopter is able to dodge it. Now, this scenario is totally inaccessible to a standard camera because with a standard camera, you need to take 2 frames. You need 2 in order to be able to estimate not just the position, but also the velocity. Having 2 frames, it means that you're limited by the exposure time and the delay between the 2 frames. With an event camera instead, we show that you can actually do this in just 3.5 milliseconds. So 10 times faster than with a standard camera. And so we were able to enable the quadcopter to fly at relative speeds up to 10 meters per second, which is about 40 kilometers per hour. And here you see basically the only information that the quadcopter is using. It's only using the events. It's not using the frame. And again, we use this contrast maximization framework. We use it to tell apart the events generated by the stationary background from the events generated by the moving ball. Okay, the remaining 5 minutes, I want to dedicate it to talk a little bit about deep learning with event cameras. So over the last 3 years, we have witnessed the explosion of deep learning methods applied to event cameras. There are at the moment 3 more common deep learning frameworks. The first one consists of applying existing synchronous dense artificial neural networks originally designed for standard cameras to event cameras. I would say that 90% of deep learning methods with event cameras do that. Another class of approaches that we started last year are those approaches that instead convert synchronous dense artificial neural networks into asynchronous sparse neural networks, something similar to sparse convolutional neural networks. However, we were able to adapt this algorithm to also work with events and also make it asynchronous. And then there is historically spiking neural networks. However, at the current state of the art, spiking neural networks performance is still inferior to the performance achieved by artificial neural networks. So in these remaining 5 minutes, I will dedicate to show you some applications of applying synchronous dense artificial neural networks like CNNs or RNNs, originally designed for standard cameras to event cameras. Now, the big question is how to feed events to a neural network designed for standard images. And the answer, you see it here. What we do, what most people do, is that we insert events into a discretized 3D volume, XYT. Okay, so we basically bind the events into voxels in space and time. And then you can apply now standard CNNs or RNNs, or whatever you want. But you just have to retrain it. So I want to show you the first application. Can we learn to reconstruct video from events? It turns out it is possible, and the results are actually amazing. What you see on the right is video reconstructed from just events. The events that you see here on the left. We are using only a neural network to do this. I will give you the details about the neural networks in a moment. Now, the cool thing about this video reconstruction is that it benefits from all the advantages of event cameras. So, it has no motion blur. You can generate this arbitrary frames at arbitrary times. And second of all, also it's resilient to high dynamic range environments. Let me show you that one by one. So, what you're going to see here now is a slow motion video on the right, reconstructed only from events, with an arbitrary frame rate of over 5,000 frames per second. And on the left, we compare with slow motion reconstructed from a Huawei P20 Pro phone. Remember, this is a 3 years old work. By the way, the code, if you're interested, was fully released. So let me show you the video now. What we're going to do is that we're going to shoot a bullet to a puppet, and the bullet travels the air at 1,300 kilometers per hour. Notice how the reconstructed video shows a much higher temporal resolution than the Huawei phone. This is thanks to the high temporal resolution of the event camera. Let me show you another application now to HDR reconstruction. So on the left, you see the raw events. In the middle, you see our reconstructed video from events. And on the right, again, a comparison against the Huawei P20 phone camera. Notice that how when the car exits the tunnel, the pixels in the phone camera are washed out, while the event-based video reconstruction instead is perfectly nice. This is thanks to the higher dynamic range of event cameras. Okay, how does it work? So we have a recurring neural network whose main module is based on UNet. And what we do is that we train this neural network in simulation only. So we have, I show you, an event camera simulator, and we minimize the perceptual loss between the predicted grayscale frames and the ground truth frames. So it's supervised learning. Now, in order to reduce the simulation to reality gap, we randomize the contrast sensitivity during simulation. This is very important. By randomizing the contrast sensitivity, we were able to actually generalize to real event cameras and even different event cameras from different camera manufacturers. This is the event camera simulator that we use. We released that also 3 years ago. It's called the eSim, Event Camera Simulator. It simulates frames, color frames, events, depth, optical flow, point cloud. So you can download it from here. And it simulates the events with microsecond time resolution, by the way. If you're interested in how it works, you can ask me during the question answering session. Now, we did a lot of progress since then. And what I want to show you, and then I'm done, is the latest results that is presented as a paper at CVPR this year. How to learn slow motion video from events and frames. So in the previous work, it was only video reconstruction from events alone. Now, a lot of beautiful things can come out if you combine an event camera with a standard camera. So we paired these two cameras by putting them side by side. We have a 3 megapixel standard camera and a VGA resolution event camera. So you see here the output of this dual hybrid camera setup. What I'm going to show you is that we have a neural network that is able to upsample low frame rate video by over 50 times with only 1/40th of the memory footprint. Let me show you again what we do, and then I'll show you the results. Basically, the input to the network is a low frame rate video from a standard good quality camera and high temporal resolution video from a VGA event camera. And we generate upsampled video using these two sensor modalities. Now, thanks to the high temporal resolution of the event camera, we are able to do amazing things. You see the results on the right, and on the left, we show you the input low frame rate video. So our work is called time lens, because it's like now magnifying in the time domain. So you can see that thanks to the continuous stream of events by the event camera, we are able to basically reconstruct these frames at arbitrary frame rate, almost arbitrary. We can discuss this if you're interested. And the results are actually super resolution, because remember that the event camera shown here has 20 times smaller resolution than the standard camera being used, but much higher temporal resolution. That's basically a key difference that you need to remember. And this takes me to the concluding slide. Where are we now and where do we want to go? So you can plot all the research papers on event cameras on two axes. One axis is the axis that shows a latency or power consumption, and the other axis shows a generalizability and quality. Ideally, we would like to have algorithms that exhibit the largest possible quality and are able to generalize to different situations. However, as you can see, the trend is rather the opposite. Now, thanks to the power of deep learning, we are moving away from geometric or in general, physics-based principles, and we are moving to things that are highly generalizable and very high quality, but are losing very much in latency and power consumption. So our goal now is to go towards this point. And with this, I would like to thank you for your attention. And if you're interested in following our work, basically follow us on YouTube, Twitter, or LinkedIn, and we have a lot of resources on event cameras and a lot of code, especially. Thanks for your attention.
Hope my clap sound works. Okay, thank you so much for the nice talk, David. Or did I pronounce your first name correctly, actually? Yeah, so there were a couple questions in chat during the talk, and I'm just going to relay them to you. Oleg asked that I was told that event cameras are analogous to how flies see the world. Is there any truth to this?
It's analogous to not just how flies see. Actually, no, it's not completely correct. How we see the world is not what our retina sees, okay? That is important. So the way we see the world is by grayscale frames, okay? However, our eyes, our photoreceptors basically mimic, are similar to event cameras because only when there is enough photons, typically about 300 photons that hit the photoreceptor, then the photoreceptor will trigger information to the brain. So actually, event cameras are inspired by humans and insects in the sense that basically they have also this asynchronous information streaming.
Mm-hmm.
Now, flies particularly use optical flow. They compute optical flow. We have to be careful. Event cameras are not optical flow sensors. They compute temporal derivatives as single pixels, not spatial derivatives over time. Okay, that's the key difference. You can compute optical flow, but that would be indirect, not directly measured by the sensor.
I see. And there's another question by Berkienko saying, is it expected to have much cheaper event cameras compared to the price of the frame-based sensors in several years? Yeah, that's actually a question that I have as well.
So if you buy the one by Selex Pixels, well, then you are going to save 5 times. So it's going to cost you $1,000 instead of $5,000. But I agree, it's still too expensive compared to a standard camera. So yeah, we're going to see a decrease in price when these products are going to be mass produced. So as you can see, in the last 12 months, there has been quite a boom because Sony, OmniVision, and Samsung, that are among the 3 best top camera companies in the world, are basically partnering or have bought event camera sensors. So event camera companies. So we are going to see a lot of progress in the next few years. I'm also working with top tier companies to actually deploy some of the algorithms I show you today in products.
I see.
And
so
this
maybe
hopefully will decrease the price a lot.
With the volume increasing.
Exactly, that's the trick.
Yeah. So Jiri in chat also asks, is there a limit to the frame rates that you can achieve with this approach?
Indeed, there is. So why did we stop? We can go in principle at the moment using current event-based cameras up to 10,000 FPS equivalent. The reason why I say 10,000 FPS is because it's true that event cameras have a resolution of microseconds, but there is jitter and there is a refractory period. This is the time that it takes to reset the voltage at the top of the photoreceptor. So, practically speaking, by including all these non-idealities, an event camera has a latency of 105 at the moment, 100 microseconds. So ideally, we can go up to 10,000 equivalent FPS. However, as now more money is going to be poured into this technology, we can expect that this latency will also shrink a lot. And again, we are able to go up in terms of frame generation.
I see. So I think I'm going to ask one last question in chat, which is related to, I guess, the event to video work. Is there any special initialization for event-based feature tracking required, or can you just start right off the bat?
Are you referring to this work or to the one about feature tracking?
I think feature tracking, yes.
Okay, yes and no, in fact. So for the feature tracking, that we call EQLT specifically, assumes that you start with some features. Yes, it assumes that you initialize the feature somewhere. For example, I mentioned before the Harris or the fast corner detector. Yes. However, there are now a lot of feature detectors for event cameras. We have one called also event fast corner detector. So in principle, you can just look at the stream of events and just extract Harris corners or even fast corners directly from the stream without reconstructing the frames. So this can be done. If you send me an email, I can send you pointers to those papers and code.
I see. Yeah, it's just a quick follow-up. I'm just curious, like, did you notice any specific points are better to track than others? Like, is the performance somewhat dependent on the key point detector that you're using?
Indeed. That's a very good question. Yeah, so the reason why in this paper we showed that we are tracking Harris corners, for example, from frames, is because they are already of very good quality. So they are very robust. They are standard corners. Because if you extract corners directly from the stream of events without passing through image reconstruction, then the problem is that as you change the direction of motion, the appearance of the corner will change. So one of the things that we experienced very quickly is that if you have shaking motion around a patch, if you extract the corner directly from the stream of events without passing through image reconstruction, then basically you're going to lose the events. Instead, if you initialize them using image reconstruction, using especially this methodology, EQLT, then you're going to be able to track them regardless of the direction of motion. Does it make sense what I'm saying?
Yeah.
Because remember, the direction of motion influences also what the events will look like. If you move the camera relative to an edge, then there will be no events. So a right corner will not look anymore like a corner, but it will look like a segment. That's the problem. So if you pass through image reconstruction or you initialize them from frames, then this algorithm will not break.
I see. It's going to have quite different characteristics from what key points are good in natural images, I guess, because of this. Nice. That's right. Interesting. Okay, I think that we're running short on time. David, you're welcome to stay for a little more while and answer some other remaining questions in chat. There's also a YouTube stream that does have people there, so you can also join there.
Absolutely.
And I'll then hand it over to Vassileios.
Thank you, guys. See you.
Thank you again.
All right, continuing. Is everyone hearing me okay? Yep, continuing to the next talk from Marc Pollefeys, who's a professor at ETH Zurich, working on 3D reconstruction stuff, lots of robotics and machine learning. Very interesting, obviously, seminal work in all these areas. And for the last few years, he's also working with Microsoft on the HoloLens, some very exciting things there on the AR and mixed reality fields. So yeah, I think Marc is with us. So looking forward to your talk.
Thank you. Let me find. Okay. that work?
Yep.
Okay. Okay, very good. So, so thank you for having invited me. I'll talk about image matching and structural motion. I'll start with the classical methods, very briefly, kind of going over kind of the classical pipeline, why features are important there, and then talk about some more recent results, and also focus on privacy and feature privacy and so on. You know, going back more than 20 years now, this was really already back then the kind of the structural motion pipeline and 3D reconstruction pipelines that we looked at. And if you look at this, not so much has changed. Still, most pipelines will actually first go through a feature detection stage. You know, they describe the features, match the features, then use geometric methods to find relative motions, do structural motion, and then typically revisit the images with then stereo matching, multi-view stereo, and from that then build 3D surface models of the environment. So that's essentially here the pipeline we set up, you know, back in 97, 98. This particular pipeline had self-calibration built in. You know, after a few years, we had also, like in 99, we had bundle adjustment built in. We had also curves and Levoy, dense surface reconstruction, and so on. Many of the elements you still find in pipelines today. Here's actually also, you know, as I realize that often, you know, students or people that join the field in recent years don't realize that maybe we could already do a number of those things, you know, a long time ago. So here, some results on, you know, from a video sequence where we could automatically process it, automatically calibrate and self-calibrate from the data. We used KLT tracking to track features throughout the video sequence. And then, you know, do the structural motion and self-calibration, and then, you know, bundle all of this, and then revisit, do multi-view stereo, actually a multi-view linking. We matched from one keyframe to the next, and then from that keyframe again to the next with multi-view, with stereo, and assemble that in a multi-view stereo that essentially for each pixel determined how far we could track in a dense way, how far we could track the features, the points, the pixels. And that resulted in these type of quite detailed 3D reconstructions of the scene. You know, they were still actually, you know, we could do these really nice reconstructions, but we had actually strong limitation. And the strong limitation was the feature detectors. So in a video, we could do KLT. That worked really well. We also worked with image sequences, but, you know, I could get good data. But if we had random people collecting data, it didn't work because you had to very carefully not move too much from one frame to the other. At the time, we were using Harris corners and then you know, zero mean normalized cross correlation to as a descriptor, or actually to, you know, not as a descriptor, but to match between features between Harris corners. And this was very, very brittle, and you had to be very careful to not move too much from one picture to the other. Of course, with video, this is not an issue, but this was really an issue when we tried to work with photo collections. Everything changed then when David Lowe came out with SIFT. And then suddenly there was a flurry of work that essentially built on the same structure for motion algorithms, but was able to essentially from more or less random photo collections where people, that anybody could grab essentially without paying too much attention, you know, could reassemble very nicely, you know, structural motion and 3D models from that. Most, you know, like probably the first here was Shafariski and Zisserman in 2000, but then most famously there was a work by Noah Snavely and co-workers on phototourism. And then, you know, this continued in really scaling this up, for example, in Rome in a Day, where essentially really online photo collections, you know, large online photo collections were reassembled through structural motion and so on. You know, in that time also open source or, you know, structural motion solutions were provided. For example, here, Visual SFM by my student Chang Wu. who received actually recently the Marc Everingham Prize for this search for motion work. Based on we were inspired by the work that was trying to scale things up, leveraging a lot of the work we had been doing on making things really fast, on leveraging GPUs to do the heavy load of computations, actually leveraging Shangchang's GPU sift, and essentially with a single PC pushed to be able to process almost 3 million images in a single 24-hour day, and essentially reassemble 10,000s of 3D models, including actually dense 3D reconstructions, as you can see up here. So continuing on that, we actually then Johannes Schönberger joined first the group at UNC, and then came to ETH and built this really nice open source SFM and multi-view stereo pipeline, CallMap, and actually for that received also the Marc Everingham Prize in 2020. The Marc Everingham Prize, to remind people, is actually a prize where somebody spends a lot of work in the community to build something useful or generate a data set that's very useful and really moves the community forward. This pipeline has been used or has been at the basis of a lot of building out of data sets, has helped actually a lot of learning approaches by providing kind of results to start learning from, et cetera, et cetera. So beyond that, I wanted to talk a little bit about new learning-based methods to find features. So there's been a lot of different approaches. Something we looked at a few years ago was to see if we could do the detection and the description of the feature at the same time with the same network. And so we did a first attempt there with my student Mihai Dusmanu, where essentially we had a network that was more a semantic network that has many different channels that would essentially both local maxima in the detection, in particular layers, would be essentially generate the detection, and then the actual the descriptor would be over all the channels, essentially the signature that you would have at that location. This turned out to actually work really nicely, allowed us to match from day to night and over a much wider range of challenging images than often done previously. One downside of this was because we use mostly a kind of pre-trained from a semantic network, this would not have very crisp detections, but typically had more smooth detections. And so the exact localization of the feature was not always very accurate. And so therefore, we looked at a way to address that. Now, what we proposed then is a completely generic method. And actually, as you can see here, a very simple method to extend essentially any search for motion pipeline, where you have feature detection, feature extraction. And so when you do, if you have a video sequence, as we discussed before, you can actually extract a feature in one image using, for example, the good features to track from Shi and Tomasi kind of concept. So you extract a good feature that you can track from image to image, and then you can keep track of that feature throughout the sequence. So you only extract once, and then you do the best possible matching in the next image. However, when we look at photo collections, we have to do the extraction separately, typically. So we extract in one image, and then we extract in the other image separately, independently, and only then do we match. But in a sense, once we know that we have extracted this feature, and those are probably matching, we can actually revisit the images, and given the details, the pixel information in this image and the pixel information in this image, we might be able to actually refine the pixel positions based on that. And that's actually a very simple idea that we decided to exploit here. Of course, it gets a bit more complicated when you don't just have a track consisting of one feature matching, another feature, just a two image match, but you have matches over many more images, so longer tracks, etc. But the basic concept was essentially, and we trained a network for that, that would essentially, given the two detections in the two images or in three images, but the basic operation was a two-view refinement, you would take the detection in both images that had been obtained independently, and now in both directions, you would aim at refining the location given the two patches. And essentially, this is something you can insert to essentially refine your detections to be more consistent using this network. Also, if you have more than two view matches, you can do this consistently over this graph and also make sure that there's no inconsistencies in the graph. So clean things up a little bit, do a multi-view refinement, and then essentially, from, insert all of this in your, before the structural motion, these refined positions can then be used for structural motion. So essentially, these three blocks at the bottom here can easily be inserted in any structural motion pipeline and yield essentially significant improvements in the precision of where the points are located. Okay, and so this was something that was particularly useful for the less accurate features, that positionally less accurate, but that we could match over a much wider range of, illumination changes or other changes in the environment. One of the reasons also I wanted to mention that is that this was also, this work on point feature detection was also an inspiration for our most recent work that we presented earlier this week at CVPR. So this is work that we call it SALT Square. It's essentially self-supervised occlusion-aware line description and detection. Essentially, the goal is to essentially both detect line segments and at the same time also describe them. The colors here, illustrate feature line segments that eventually will be matched over the descriptor, and also have awareness of the occlusion in the matching. So have a matching scheme that allows us to handle potential partial occlusions of the lines, as you can have, essentially this part of the line is not visible in this image here is occluded. So why do we want to look at bringing in lines? Point features have been doing really well. But of course, in some structured man-made environments, it's actually sometimes very difficult to find good points, and in particular points that are interesting enough so that we can properly match them from between images, especially when we're talking about wide baseline situations, as you see in this example here. So on the left is super point matching, which is really struggling in this case. On the right, we have essentially line matches obtained by our method. So the contributions are essentially in this work are joint line detection and description. It's a self-supervised approach that's inspired by SuperPoint, and it's a repeatable line detector that's also robust to where the matching is robust to line occlusions. Okay, so the idea is, as we said, inspired by the approach proposed by SuperPoint. So essentially, we start from simple synthetic scenes that we render with known line locations. So this part, of course, is supervised, but it's purely synthetic, where supervisory signal is pretty trivial to obtain. So we generate that, we train our deep net to essentially find the junctions and have a heat map of where the lines are located. Then we have a line detection module and essentially predict line segments. And so we do the training here end-to-end on this pipeline. And then in the second stage, the self-supervised part is now essentially using homography adaptation, also similar to essentially the SuperPoint approach. So starting from an image, we will actually apply a number of homography warps to those images. We apply to all those the same network. We essentially get our point, junction detection and heat map detection for all three. And now what we want is to essentially obtain consistent results here. So we know the homographies, of course, we've applied those ourselves. So we can undo the homography, or in other words, we can take the results and warp it back to the original, reference image. And essentially, this now aggregates the three independent detections here in this example, or many more in practice. And then in this, we can apply a line detection module and get this. And we use this as ground truth. By essentially having many of the detections all merged together in a map, even if one of them fails, if some of them fail, we typically have a robust detection because we do the joint voting here, we aggregate. And so essentially this tends to, even if some of those detections fail, by having this aggregation, we tend to get pretty good results. And then we can feed those back as ground truth essentially, and do essentially backpropagation through the network to improve all of those all of those networks here, back to the correct results. Okay. And then you could iterate that a few times. In practice, actually doing one iteration of this is typically fine. And so, so essentially we have the, this was the part for the detection. And then there's also a descriptor part, which is essentially along the line, along every line segment, we'll essentially extract, by looking at points at regular intervals, we'll extract a descriptor. Here is showing that a little bit. Also, essentially, when we have two junctions detected and we have this heat map, we'll actually use a local maximum search to refine the line location and get the regular sampling there. And then for doing the occlusion-aware line matching, we have a number of points here and we have a number of points here, but it could be an occluder. And so therefore, we'll actually, for the points here and the points here, we'll establish, essentially a matching matrix here, potential matching matrix, and apply dynamic programming here to find the best possible path here so that we can actually handle occlusions if there were occlusions present. Okay, so here's some results. So you can see that even with, wide rotation of change of viewpoints here on the homography, it works quite well. For the detections are quite stable, not perfect. You see actually the red lines are showing the ones that are, present in one, but not in the other. And here are then some results essentially on the YorkUrban dataset, which is a reference dataset used in line detection work. So I can see here, so actually most of those methods, many of those methods are based on LSD line detection. You can essentially see here the results, the amount of lines that get detected, and then here different metrics that were applied in this data set here. And then also here, the one with last column essentially shows you the compute time for this. So our method is reasonably fast. The fastest method is LSD, which is a very classical method here. But you can see that in terms of quality, our method here without or with non-maxima suppression, depending on what you prefer here in the metrics, one or the other tends to be better. Here also, if we look at line description, and we look at the precision versus recall of all the different methods, and actually also notice here we have our method where the descriptor is used, but the detection comes from LSD lines as an ablation, essentially. You can see that we outperform all of these other classical methods, doing already much better with even based on LSD lines, or without non-maxima suppression performs over here and over here, slightly better than LSD. And then with the non-maxima suppression, we actually really do significantly better still than the classical methods. This is on the wireframe data set. This is on the ETH3D data set where we labeled some ground ground truth images manually. Here's some examples. Also here, you can see the robustness to occlusion. So this data set, we actually applied here a number of occlusions. Here, random occlusions showing up and showing essentially that our method, based on the amount of occlusion per line, our method stays much, performs much better in the presence of occlusions. Okay, so here's some video demo with occlusion. You can see here on the right the person applying occlusions to the lines, and you can see that mostly the lines are still detected and keep the same color as on the left. So in other words, are robust, can do robust matching even in the presence of occlusions. Here's then an example of also as you move around and change viewpoints, but partially quite drastically, you can see that actually most of the lines keep the correct labels and keep being detected appropriately. So we get some pretty good invariance to viewpoint. And here's actually also a small demo showing that you can use this for reconstruction. So this is first the point reconstruction, and then here with the lines. Also one example of the lines immediately bringing you a lot more context than just the pure point reconstruction. Okay, there's still a few limitations. Our endpoint localization is still not super precise. It's comparable to LSD, but we would like to improve it. And then, so essentially, this is one of the areas that we're focusing on in future work or in ongoing work. So in other words, SOL2, SOL Square is the first deep network for joint line segmentation detection, segment detection and description. It's a self-supervised method for line detection, and this can essentially be trained on any data set of real images where you have good amount of lines, because we start from synthetic, but then we essentially are self-supervised by applying these homographies and getting aggregation. We typically get enough signal to let the network improve itself without needing supervisory signal. And we get pretty good, robust matching, pretty robust to occlusion, and essentially achieve the state of the art there. If you're interested, you can find a paper and the code at those, using those QR codes. So next piece of work I wanted to talk about is essentially Pixlok. It's an image-based localization approach, which essentially is doing end-to-end learning. And as you see, it's a collaboration between many different teams. So essentially, the goal is to have a query image and then essentially answer the question of where this image was taken in this large environment. Okay, so first thing we do is essentially an image retrieval method, where we use existing methods that are able to essentially find that this image is is likely to be similar, close, have been taken close to this image. As I explained before, some of those there's actually pretty good methods that can match across wide range of illumination and so on, and find these kind of images that are likely to be matching. But the question is, how do we now find the best possible pose here? Okay, so essentially what Pixlok will do is determine the correct rotation and translation relative to the 3D model or to the previous, to the reference pose, reference image that was provided or that was found. Okay, so classical methods would work as follows. They would do detection of features, description of features, then matching features to the 3D model, the reference 3D model, and then use a solver to essentially do a geometric computation to compute the pose. What's nice about those classical methods is they're scene agnostic, they have very good generalization, and they're interpretable. We know which features match which, and how, from that we could compute our pose. We can have uncertainty on the pose, etc., etc. What's annoying is that it's typically these are relatively complex pipelines to really achieve the state of the art. There's a lot of tuning. A lot of things have to be done, engineered quite well to achieve state of the art. The other type of approaches nowadays, there's a lot of work going on in end-to-end localization methods, where there's essentially first blocks that extract features, and then two types of approaches here. There's the pure pose regression. Think of methods like PoseNet and inspired by PoseNet, which will directly regress the pose. And then there's methods that are more hybrid and that will actually do 3D point regression and then still use classical solvers, more like methods like DSAC, etc. In particular for pose regression, if you're interested in those, or if you look at those, if you want to know why those have strong limitations and actually really yield quite poor performance and actually don't really outperform just finding the closest image in your database, then I recommend you to read this paper that we published at CVPR 2019 that talks about those limitations. But I won't further expand on that. Essentially, the method that we are pursuing here is essentially aims for end-to-end, but also will essentially leverage classical 3D geometry and bring those things together. So the approach works as follows. We essentially have an image. We have a CNN that will extract features. And the question is, what is the rotation translation to an existing explicit 3D model? And we also need a reference image that is aligned, that is somewhat close, so that has essentially overlap in the features, that there's, good co-visibility between a number of the points, what the content seen in the reference image and the query image, as is the case here. But this can be done over quite significant changes of illumination. But of course, you have to see the same thing. So the first thing is to find an image, a good reference image. This is not what we'll talk about here, but assuming that we can use essentially image retrieval methods to find a good reference image that sees the same stuff, and we have our 3D model, then this method will essentially end-to-end train the method to retrieve rotation, to in the end be able to retrieve rotation and translation. Okay, so how does it work? Well, we have feature extractor. We actually have this at multiple, at a fine and a coarse level and a medium level. And so we might initialize rotation and translation, for example, from the pose of the reference image, assuming that is probably a pose that's quite close to the to this image or relatively close. And then we can essentially project, those features here, the particular 3D points. They have a position in the reference image, and then we can also project those. Given the current pose estimate, we can project those in the query image, and then we can essentially use optimization to minimize the discrepancy between the feature descriptor, the feature descriptors at the different levels that we have in the reference image and that we have in the query image. Okay. So we'll essentially aim for getting feature alignment here by changing the pose to get the features here and the feature descriptors here to essentially correspond as well as possible. Okay? And so essentially we'll backpropagate through this here to really find, to develop features that make sense and allow to bring things in correspondence. Okay? So the nice thing about this approach is it is an end-to-end method, but it is scene agnostic. It just learns essentially, the only thing it focuses on is what are the features, what features should I, it essentially pushes everything on this CNN here, which is a feature descriptor. So it's scene agnostic, generalizes well. That's essentially the same thing. It's quite accurate and it's interpretable because you really have essentially correspondences at the end. Okay, so here's an illustration of how this works. So you start here from an initial pose. And then, or actually, let me restart this. So you have here the reference image, you have the 3D model. You will essentially you have here the 3D model projected in the reference image. For each of those locations, you can essentially read out at every feature, you can read out the feature descriptor that was computed, or the CNN essentially read out the descriptor for each of those feature points. And then we can do the same in this image. If we initialize from exactly the same position, we'll have the same point locations here, we'll read them out. And for example, here we'll find a pure sky image, and we'll see that this is not good, and we'll be looking for, in what direction do we need to move this feature, or how do we need to move the pose, so that this feature will move to a location that is more likely to correspond, which would be, let's say over here, right? So this is essentially how it works. And the network will, the optimization will essentially move and will from coarse to medium to fine will essentially refine to the correct location here. So the approach goes through these 3 stages. It's essentially also what's really important is that it has a feature descriptor, but it also has a confidence. So our method would actually not only learn the descriptor, but we also learn which part of the image makes sense to try to put in correspondence, and which parts are maybe objects or things that actually are unlikely, that we're unlikely to be able to match for good usage. What we'll see is that, for example, here you see you have a car, and so the network, what we observed there, the network was actually able to learn just from the localization task, was able to learn that cars were just no good for localization, and so suppress those in the confidence map. So that we don't try to match it, but essentially just ignore it. So we have a feature descriptor here, but it's ignored because of the confidence map. So essentially we have this residual weight. So notice we have it both for the query image and the reference image. We have those both descriptors, and then we look at moving the pose and essentially minimizing here the discrepancy between the descriptors, the corresponding descriptors based on the pose. So in that sense, you should really look at this as a direct method. But a direct method that doesn't look at the original, at the pixel locations, but really a direct method in this feature, in this weighted feature space, confidence weighted feature space, essentially, right? And of course, we do that at the different stages. So we first converge at the coarse level. Once we're there, we have a new pose that we can initialize the medium level with. And from this pose, we can initialize and compute then in the fine stage, a final pose, coming out of the algorithm. Okay, and so we have losses here at each of those stages, and we can do the training. And then what you see here is essentially this, from an image like this, that we have, when we train from, and we have images like this, where there were cars and so on, the network would have realized that these cars between different pictures, that we have as with ground truth poses, we would have learned that these cars are completely useless in matching, essentially without telling it that these were cars or anything like that, but just because they're useless for matching, because they tend to never, be found back in the corresponding images at the right place. And so those features essentially turn out to be useless. On the other hand, for example, here, we notice that features at the top here, at the silhouettes of the trees are actually in these type of images quite useful for matching. Or here, the more permanent markings on the road, for example, are also good features to work with. Also here, another example is these highly repetitive features are essentially being suppressed. While then, larger features that are more stable that can be used for matching here at the windows, those are actually, strengthened. And also here, very clearly, you can see that the silhouettes of the buildings are very strong features and strongly used. Okay. So all of this is essentially learned automatically by doing the end-to-end learning on the pose computation phase. And so here's a few examples showing you how robust this is. So notice this is the reference pose that we start from, and you see that essentially it nicely converges from that original pose that's quite far and quite wrong to then the correct pose where the features are then very nicely aligned and precisely aligned. Okay. Here's another example. Also, notice the day-night matching is not a problem for this method. Also, generalization. So this was trained on outdoor scenes, and then this can directly be applied here out of the box on indoor scenes also. Here's a few more examples. So now let me switch to the last part I wanted to talk about, which is essentially privacy preservation in structural motion, in localization and structural motion, localization mapping, and then also particularly I'll talk also about features descriptors. Okay, so we've been doing quite some work in this space. Started by essentially trying to preserve the privacy of a 3D model while still enabling localization. So we proposed a 3D line cloud for that. Then we actually turned it around and we said, well, can we, if we have a 3D model in the cloud, but we want to upload images, can we avoid uploading feature descriptors and locations of those 2D locations of those features, so that you can actually, from the data, from the 2D features plus locations, you can almost reconstruct using inversion attacks, you can essentially reconstruct the original images. So can we kind of send something up that will better preserve the privacy? And so we turned it around and enabled localization from this privacy preserving, uploading of privacy preserving data to the cloud. We also have been doing, essentially then we've extended that to, can we actually not only given a map do this, but can we actually do structural motion from this type of data in the cloud? So without having an initial map to start from. We've extended that actually at CVPR for uncalibrated methods. There's also been then work by others actually picking up on this to actually use line clouds for doing on top of an existing line cloud, to extend the line cloud and do essentially tracking and mapping on the line cloud. And of course, there's also been very interesting work by Thorsten Sattler and collaborators on actually looking at, maybe those representations still have privacy risks, and so in some circumstances can be attacked, and that was actually very nice work presented here also at CVPR. So what's the concept here? Well, normally you define a point. A point is defined by three constraints, three planar constraints. Let's say it would be three linear constraints on the point location in a 3D space, right? Typically, it's on this X, this Y, and this Z plane. Is the typical, but you could just use any other three linearly independent planes to define the location of a point. Okay, if we would drop one of those constraints, so we drop one of the three planes, then we're still left with two constraints on the location of the point. Okay, but then the ambiguity of the point is essentially along a line in space, as you see here. So in the first case, if we have a 3D point, we project it in an image. And we have a 2D point location there, we essentially have two reprojection constraints coming from a single 3D point. If the single 3D point gets relaxed to a line, then the back projection constraint still gives us one constraint. The point that we detect in the image should still be located on the projection of this line in the image. That's still actually one geometry constraint. So meaning we still have geometry constraints without needing to reveal the precise position of the point. Okay, so that's the key idea that we use to essentially work with these line clouds instead of 3D line clouds, instead of 3D point clouds that reveal the 3D structure of the scene. So here you can see that if you look at this line cloud, you can't quite easily recognize which scene this is. But if we switch to a point representation, it's of course pretty trivial for people to recognize the location. So here's another landmark. You can try to guess if you haven't seen it before. Try to guess which famous landmark this is. And so notice these line clouds, we can perfectly use those to allow precise relocalization with respect to them. Okay. Here's the last one. I can try to find it. So this is Notre Dame. Okay. So the method is essentially as follows. This is classical, traditional P3P for pose estimation. We essentially switch to, in the most generic sense, here, most generic version of the algorithm, we now need 6 because we only have one constraint per point. We have 6 lines in space, and we have 6 points in the image. And essentially, this now is our minimal problem, is a P6L. Notice that it's actually 6 lines having to intersect with 6 lines. This is actually was solved as a relative generalized pose problem. And so we could reuse existing solvers. More in general, actually, there's plenty of different methods that can be used depending on the different constraints and depending on knowing the vertical reference direction or not. So if you have an IMU, you know the vertical orientation, etc. So the P6L is not super practical, and you lose quite some accuracy, but actually many of the other methods are almost as accurate as the classical method, as the classical P3P method. As you can see here, the methods, the full line is our method, privacy preserving method, the dashed line is the classical method. And you see there's not much of a difference, especially knowing that we only have half of the constraints than the classical method has available. So the key is essentially that this method actually really works, and some of those methods are actually really fast and can be implemented essentially without a real penalty. Same thing is then we looked in the other direction. Can we actually do localization by sending over image data to the cloud, but in a way that it cannot be inverted? Same idea. We, instead of sending over to the point locations, we send over line locations. The lines are, randomly drawn lines that go through the original points, and that essentially allows to have then each line here, if you back project it, corresponds to a plane. And so now if you have 6 planes that have to, essentially go through the 6 points in space. So here we have 3D points in space, but we only send over these kind of line constraints. Then you can also compute the pose of this camera from only these line constraints. Okay. Why is this interesting? Well, all of the points that existed in the map and that you match, these in the end you can still reconstruct. But all the points that now don't have a corresponding point in the map because they're transient points, those are the ones that are typically privacy concerned. Well, those points, they're not in the map. The points that are in the map, you have them already anyways in the cloud, so there's nothing special about them. But the points that don't exist in the reference map, that are the ones that might be privacy concerning, those can now not be reconstructed because each of those feature points, we only know that it's somewhere along the line, but we don't know where it is. And so the reconstruction looks like this, which has the part that was in the map reconstructed, but the part that wasn't in the map is essentially is private. Here's a few more examples of this method. Then very quickly here, essentially we looked at, okay, if we have a 3D map in a cloud, or if we have data, like we can essentially work. So we have a 3D map, we can generate a privacy preserving representation within a line cloud and so on. But is there a way that we can upload only privacy preserving data to the cloud and, from scratch, do essentially a crowd-based mapping in the cloud? So this is not so simple. The generic solution would require us to solve a generic quadrifocal tensor as the origin, the minimal solver. So we need 4 images with, I think, 15 points or so, 15 lines between the 4. This is essentially very complicated to solve. And you need to solve, very complicated polynomial equations, high order, to solve this problem. However, if we have the vertical, or if we have a reference direction, then we can do some tricks, and we can actually simplify the problem. Instead of solving 4 images quadrifocal tensor, we can actually go to 3 images and solve a 2D structural motion problem by having these reference directions. We only have to solve, let's say, the ground plane structural motion problem. So that's a 2D problem that only requires to solve a trifocal tensor, which is much, 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 much simpler to solve. It's actually only 7 correspondences in 3 images, and it's a linear problem, no internal constraints. And so that is enough to initialize the problem. There's a few more tricks to this, which I'm not going to go into, but once we can initialize, the structural motion, and then once it's initialized, you can easily triangulate simply by back projecting 3 planes, which allow you to triangulate a point. And we can use our pose estimation method that we already had before to essentially, find the pose. And so as we can iterate between triangulating points and estimating the pose, once we are initialized, we can easily keep extending the reconstruction. And then, also we can bundle everything. And so we can actually get quite accurate reconstructions. This is how it looks like. So this is the classical, a large photo collection, classical structural motion. And we see that if we take all the features and reproject, and do an attack, privacy inversion attack, we can find quite some problematic data. And then in the privacy-preserving search for motion, you see that we can get a nice 3D reconstruction, qualitatively same quality 3D reconstruction, but you could see that all the privacy-concerning information in the images had disappeared, could not be reconstructed anymore. Okay, we've actually just at CVPR here extended this to also enable uncalibrated privacy-preserving location and mapping, and we show here that essentially this method is still quite accurate and allows quite accurate reconstructions and post-estimation from this on well-known reference data sets. Okay, so to finish, to wrap up, I want to also quickly talk about work that was presented here at CVPR, which is on privacy-preserving image features. So you've seen before privacy preservation on the geometry side. Now we actually try to use the same concepts, but on the feature side. Okay, so a feature is also represented as a geometric entity in a high-dimensional space. So a feature typically, with SIFT or other features are essentially 128 represented as a 128-dimensional vector, often actually on a hypersphere. So essentially, descriptors are points on this 128-dimensional hypersphere. So there's many applications where we'd like to also not only preserve the privacy of the geometric reconstruction, but also preserve the privacy of the features that we have detected. But of course, still be able to match them, right? So here also the concept is the key points with their descriptors so we've seen how we can preserve the privacy of the key points by drawing lines through them. We can actually apply the same concept to the descriptors in this high-dimensional space. Okay, so essentially what we'll do is instead of having a single point, we'll generate subspaces, affine subspaces in this hypersphere, which will make the inversion much, much harder, okay, as you can see here. So how do we do this? Well, essentially, if we have here a particular vector D, the feature that that we have, that we want to essentially make hide so that we can preserve privacy, what we'll do is we'll add some additional features to it. Okay, so we could do something like this. So we draw a line through this, a subspace, and affine subspace in this high-dimensional space, going through the point, but kind of in a random direction. Now, there's a problem with this random lifting, which is that this might not actually intersect any other, real set of existing feature points. And so then you can have a pretty simple attack, which is simply to have, look for the closest existing kind of realistic features to this line. And then if you do that, you can actually typically find back, often you can find back the original feature descriptor, okay? Because the space is not fully covered, essentially. So what we do is actually switch to a more adversarial lifting, which is pick another cluster of existing descriptors that we know exist as descriptors. And so we're sure that there's ambiguity now, because this is our actual descriptor. This is some other cluster of descriptors. And by connecting those, we now have a subspace that at least has two clusters of real existing features. Okay, so here there's plausible ambiguity. Now, of course, it's susceptible to collision, so we have to be a little bit careful with this. And so the trade-off we typically do is a mixed random and adversarial. So our subspace, we can expand it to both go through some existing points, but then part of the dimensionality of the subspace can actually also be random. Okay. So for being able to do matching, normally, in the space, in this 120-dimensional space, you typically just compute the distance between the descriptors, and this is essentially how you do matching. In our case, because we now lifted this to subspaces, we have to do point to subspace distances. This is actually quite efficiently done through projection, and this distance that we measure, the distance to the subspace, is essentially a lower bound for the distance to the actual point, but in practice pretty close. And so this can be used as essentially as a metric and as for matching. When we have actually privacy preservation on both sides, then we have subspace to subspace distances, which can also be computed. This actually is a little bit more complicated and requires you to solve a linear system of equation here, but it can certainly be done. Okay. and also here, this is essentially a lower bound for the actual distance between the points, as you can see here in the illustration. Okay, reviewers and actually, if you think about this, would say, well, there are maybe other methods to preserve privacy of descriptors. You can use homomorphic encryption to encrypt those descriptors and then still essentially compute on those encrypted descriptors, immediately compute the distance between them. But it turns out that those methods are actually very, very slow for the purpose of image matching, because the problem is really that what we have to do is, if we have 1,000 features per images, those are 128-dimensional vectors, we really have to do 1 million comparisons. And so that becomes essentially unaffordable. So matching a pair of images would take 16 minutes with the most efficient homomorphic encryption methods, while our method here, subspace to subspace or point to subspace on GPU, is very, very fast. It's really in a few milliseconds for doing the whole image-to-image matching. Even on CPU, it's doable. This is still a fraction of a second. There are some limitations on how large a subspace can be on GPU for subspace-to-subspace computations. But point-to-subspace computations, we can actually also go quite high here. Okay. Here's some examples of this, showing how our hybrid lifting here essentially allows us to really completely resist. There's different types of attacks. Nearest neighbor attack. This is perfectly tackled with the hybrid approach that also has some adversarial examples built in. There's another type of attack that that essentially really tries to retrain and learn how to invert this end to end. But even this one is mostly countered, and you can see that here you can still recognize the person with the right descriptors, or with the random lifting that is open to adversarial attacks. But if we do this sub-hybrid lifting here, we actually, even this person is already barely recognizable. And if we go a little bit higher in the dimension, there's nothing anymore to be recognized. Okay. Here showing that, so this shows that it's actually good in privacy, against privacy attacks. But does it work? Do we still get good results? And here we essentially show that we get actually quite good results. We don't lose too much on when we apply this. And also, so notice here, there's only a little bit being lost when we do things. Also, here we can actually do large-scale structural motion with this type of privacy-preserving feature descriptors. And then as a last thing here, something that's actually quite interesting is that this privacy preservation can also be adapted, for example, used in face recognition. And here's actually something, what we do in the privacy preservation here is we can recognize a person, but in a way that from the descriptor, from the face, the 120-dimensional vector that describes the appearance of the face, we cannot recognize the gender anymore. So normally, if you have a descriptor of a face, you can essentially almost perfectly recognize the gender because you can recognize the person from that. What we can do is make this, in particular with our hybrid method here, we can achieve essentially 50-50 chance on gender. So perfect preservation of gender identity, appearance of gender. For race, we can't get it perfect. So there were 5 races. So random would be 20% if it's fully balanced. But we get pretty close to, it's not perfectly random, but it's pretty close in terms of protecting the race identity of the person from, in those vectors. So we can allow to recognize a person, but in a way that that vector that is provided doesn't allow, to the reference vector of the person, doesn't allow to determine which race that person has, for example. Okay. Just to wrap up, as a preview, essentially we're working on an ETH Microsoft dataset that will contain a lot of data for essentially your aim is lifelong type of mapping scenarios, and have essentially high accuracy ground truth for poses in large and diverse environments. And so if this is something of interest to you, look out for it. We should have some first data sets or parts of the data sets available in the coming, probably in a month or two. So do look out for it. Okay, to summarize, I talked about classical structural motion pipelines and the importance of features in those. Then we talked about joint detector and description for points and for lines. And then also end-to-end learning for features for visual localization, including also this, how useful a feature is essentially for visual localization. Also get this confidence learned end-to-end. And then we, finalized at the end of the talk, I talked about privacy preservation in structural motion and in image features. So thank you for your attention. And I'll be happy to take questions if we have any time left, but I guess maybe not.
Thanks, Mark. That was great. Great presentation, lots of information there. I think we have time for two quick questions. I think both of them are related to Pixlock. Remy already answered one about Solid Square in the chat. So the first one is regarding the confidence map. This is from Emmy from YouTube. Regarding the confidence map in Pixlock, it seems that it also fires up quite high in the sky. How is this affecting the approach, and what is the comparison to the traditional feature-based methods, where I guess the author means that it wouldn't normally fire in the sky?
Yeah, so let me go back there. So it does fire a bit in the sky, but it's mostly really at the edge of the sky between. So it doesn't fully suppress the sky, but you're right. So I don't think this really affected it. So the reason is, let's see, wait. Yes, so actually the reason is that the sky is compatible with the sky, so it doesn't need to be suppressed. If you understand what I mean, so essentially it's actually useful as a kind of silhouette constraint in a sense, right? So the sky should match the sky. A car should not, the front wheel of a car, in another image will not match the front wheel because there's another car that's at a different place and this and that. So those just don't work. The detailed bricks, they will be misaligned, and so they are not working or so. But the sky is just a uniform sky. Typically, it's essentially learning that it's the sky, and it's useful to actually have the sky as a kind of silhouette constraint. What you should not have is have a building show up where in the other image there's a sky. So it's actually still a useful constraint. It's not a good thing to, just by itself, it's not going to give you a precise location. But when you align, the sky should align to the sky. And also, there's no feature points there. So it doesn't get negative information also like that. There's not much information there anyways, and it's not incompatible information. So it can be, it's useful information to have. You're not going to get you don't have to suppress it, right? So the ones that are dark have been suppressed because they didn't work out, right? You couldn't, you had the right alignment and they weren't matching. This doesn't happen with the sky.
Okay. Yeah, and there's a second one, which is how important is LM pose optimization? Would direct optimization work?
I think, I think, I'm not sure exactly because I haven't tried it out. Myself, so this would be more something for Paul Eduard. But I think it's just a good optimization. I think direct would probably, just gradient descent or something like that would probably also work. I think this is a little bit faster and more effective, but I don't think this is fundamental.
Okay.
Paul Eduard would be one, answering that.
Thanks again for the great talk. And thanks again.
Thanks.
All right, moving on. I think our next talk is from Daniel, Perceptual loss for robust and supervised homography estimation.
Yeah, hi, hello. Now the question is if you can hear me.
We can.
Yes, we can.
Okay, and the second question is if you can see my presentation.
I see myself.
Okay, so let me just try to reshare it one more time. Okay, and now?
Now we see two screens.
Two screens. Okay, so let's just switch off the second screen. Okay, and
Nothing yet.
yes, just give me a second. I have some problems. Your browser is preventing access. That's weird. Okay, let me just try to re-enter. Okay.
Sure. We see you now.
Okay. Hi guys again. Yes, but I need the ability to share.
Oh, you are not co-host. I guess. Let me see if I can do that. I don't think I have that option. We might need Kwang to do that. Otherwise, if you share the slides with me, I can try to present them for you.
Let's try.
No, it should be done. It's good. We see you now. You can start. Thanks.
Great. So now you can see my slides, right?
Yes. Yeah, we can.
Awesome. So hello everyone. My name is Daniel, and I'll be presenting our perceptual loss for robust unsupervised homography estimation paper. And this work is performed with Alaha Erani and Bahram Zonos. Let's start with the fundamentals. Homography, when we have a pinhole camera model assumption, a homography relates any two images of the same planar surface in space, or any two images produced by pure rotational movement of the camera. One image called source can be transformed by a 3x3 homography matrix H as if viewed from the target viewpoint, from the other viewpoint, and this other viewpoint we call target viewpoint. So basically we've got the homography matrix is described by 9 numbers, but up to the scale, we fix the scale of this homography matrix, and we have 8 regression parameters that we can regress. Traditionally, homography estimation was performed using non-learnable approaches, either in handcrafted, either in pixel space, and those methods are called direct, or in handcrafted feature space like SIFT or ORBT, and they are called feature-based methods. So feature-based methods usually perform better than direct methods. However, their success depends on the quality of those features and the content of the image itself. If we've got image with poor visual information, like repetitive structures or scene without plain images, then those methods will obviously fail. So recently, with the advancement in deep neural networks, the tone proposed a CNN architecture trained in end-to-end fashion. And the idea was to directly regress those 8 parameters of the homography. And the performance that this method achieves is similar to traditional feature-based methods. A more effective approach was proposed by Zhang, and the problem was formulated as per pixel offset regression. And yeah, here we've got more supervision signal, so the method achieves better performance. However, both methods are often, supervised methods are often unlikely to be used in real-life scenarios where the ground truth labeling is costly, and that could be the case with homography estimation. So now we can go to unsupervised methods, and first one was introduced by Nguyen, and the approach is split into 2 parts. First, we use some CNN to estimate the homography parameters. And then the estimation is learned by comparing the per pixel intensity of warped image and target image. And this warped source image is warped using estimated homography. And models trained using this formulation perform really well for images with big viewpoint differences, so with wide baseline, but are not robust to illumination change because we are using photometric loss, basically. And so if we want to find a homography between images taken, for example, far away in time, this method will probably fail. In contrast, Zhang, in recent work, by learning the feature representation used, and this feature representation, the representation is used for both homography estimation and image comparison, achieved robustness to different lighting conditions, but only for images with small baseline. So to sum up, unsupervised homography estimation for both big viewpoint and big illumination change is still an open problem. So here we present a novel unsupervised framework for homography estimation, and the key insight is to decouple learning representation for both homography estimation and image comparison by using a dedicated loss network. So we are not using those. So the first part is learned. In homography estimation network, we've got parameters of a neural network of whatever model we are using, and those parameters are learned. And in the second stage, second part of the network, it's an end-to-end approach. We don't have any learned parameters. So the homography is learned implicitly by comparing the images in feature space produced by loss network. So in the evaluation, I will show it just in a minute. We show that this approach is robust to both changes at the same time. So using additional assumption that the homography between images should be invertible, we can compare word source image and target image and swap the roles. So then we try to estimate the homography from target to source. So finally, we call our loss function bidirectional implicit homography estimation loss by homie. So our contributions are as follows. First, we introduce a new perceptual loss by homie to be used in unsupervised setting, which decouples homography estimation from representation learning for image comparison. Then we propose to use an additional photometric distortion step in synthetic COCO dataset generation to evaluate the robustness of homography and estimation to big illumination viewpoint changes, which is more aligned with real-life scenarios when we have those two things at the same time. And finally, we achieve state-of-the-art performance using our bihomie loss on both SCOCO and our modified version of it, PDSCOCO, for unsupervised homography estimation. So now we can take a look a bit more in detail in the architecture. The framework is composed of two components. First one is called Homography Estimation Network, and this network can be realized by any architecture able to produce a transformation matrix, HST. So we can use any other backbone in the literature, and it will work fine. And possibly when the new backbone will came up in the research space, it can still also be used in this framework. Second part of the pipeline, we use this estimated homography matrix to transform source image IS into IS prime here. And rather than directly minimizing the distance between IT, so the target image, and IS prime, we can encourage the network to simultaneously push it away, push IT away from original IS image in triplet fashion. And we also can use visibility mask. It's not a non-alienable mask. So we only want to apply the triplet loss on the pixels that could be visible on both images. And the loss is inspired highly by Zhang method, but here, instead of learning the feature space to compare the images, we rely on perceptual similarity of high-level features extracted from pre-trained loss network. And in our case, we use ResNet34. And as said previously, we can additionally repeat the procedure for swapped inputs. So the final bihomie loss is a composition of two ihomie losses for both directions and a regularization term that forces or encourages those homographies to be invertible. Now, in terms of dataset, homography estimation is, especially in the deep learning space, is often trained and tested on synthetic COCO dataset introduced by Teton. However, it does not model photometric distortion present in real-world images, such as contrast, brightness, or saturation changes. Thus, we propose to use an additional data augmentation step in synthetic COCO dataset generation, where we, at the very beginning, additionally model illumination changes by using data augmentation techniques used in SSD object detector. So first, to briefly go through this data augmentation step, we first randomly adjust the brightness of the image. Then random contrast, saturation, and hue noise is applied. And finally, we swap the color channels of the image with probability of 0.5. And such a photometric distortion procedure is applied to the original image independently to create source and target candidates. The rest of the procedure is the same as for SCOCO dataset generation. This is like a generalization of SCOCO. To get back to SCOCO, we can change distortion step to copy, and we've got synthetic COCO dataset then. And so in terms of the training details, we believe that we should give all the methods the same training budget to so the comparison could be fair, and we fixed most of the training settings. And also we want to be sure that the accuracy of homography estimation comes from the better design, not from the better backbone. So if needed, we modified the homography estimation network, the backbones, to use ResNet34-like feature extractor. All methods were trained using Adam optimizer with batch size of 64 and for 90K iterations. The initial learning rate is decayed by a factor of 10 every 30K iterations. And as I previously mentioned, we use also ResNet34 as a fixed loss network G. And features to compare are taken after first residual block. The homography estimation quality is reported using mean absolute corner error, MACE, and for each of the settings, we train 3 independently initialized network and report mean and standard deviation of the quality, test quality. So coming to results, current unsupervised approaches, this is Nguyen and Zhang, give slightly worse performance compared to supervised methods on SCOCO, and this is what we could expect because they don't have the supervision signal. However, when we introduce both illumination and viewpoint changes at the same time, no unsupervised method can converge. And what we mean that we started like 20 different training sessions, and none of them can converge to any satisfiable result. And our Vassileios achieves comparable or better homography estimation performance than supervised methods on both datasets for any tested backbone. Now, so this is only one version of the dataset, BTS COCO, with very big data augmentation. But we can, because this dataset is artificially created, we can produce as many as hard datasets as we want. So here we want to understand more the behavior of different methods compared to bigger in terms of bigger viewpoint and photometric distortion. So we can simulate any dataset using those two things, and we have parameter ρ, which tells us the viewpoint difference between images. And we have the photometric distortion parameter delta, which tells us how much distortion those images have. So the bigger ρ, the more viewpoint change, and respectively the bigger delta, the more illumination change between input images. So now the method of Nguyen based on photometric laws is pretty robust to big viewpoint changes and viewpoint changes on the x-axis, but is not able to produce any reasonable result for big illumination distortion. So this is the first two rows on the top. So the model cannot converge for those data sets with big illumination changes. On the other hand, Zhang method is highly robust to illumination, but only in the first column. So only for the images with small baseline. The more we warp the images, the less illumination robustness this method has. And in the end, and of course, all those numbers are reported in MACE, mean absolute corner error. And as we can see, our bihomi loss is able to produce reasonable results for the whole space. And so now we can ask some additional questions about this loss. For example, how important is freezing the loss network for effective homography learning? As you can see in the table, fixed loss network performs better. Those are the first two rows. And one of the possible reasons is that with fixing the loss network, we can use bigger learning rates, which in the literature is sometimes connected to better convergence. But even for the same learning rate, 1e minus 3, then freezing is the loss network is still a preferable policy. So there's something else, something more. Maybe when we unfix it, we break those fine-grained features learned on ImageNet. So that's only, of course, that's only we can hypothesize now. Other question is, for example, when we use loss network trained on ImageNet, the whole method could be could have suboptimal results on other on ImageNet or on images trained with different, vastly different distribution than ImageNet, for example. So here we wanted to test it. So we took FLIR thermal dataset and preprocessed it in the same way that SCOCO is preprocessed. And although those thermal images are vastly different than the color images, the loss network was the loss network was trained on, so ImageNet, our bihomi loss is still achieves better performance. So it seems like those features trained on ImageNet are pretty domain independent or pretty general. And we have much more ablation study in the paper, so please take a look, and if you can, and we can always email us, and we will be happy to answer those questions. So to conclude, we presented an unsupervised approach to homography estimation that is robust to big illumination and viewpoint changes at the same time. We showed that disentangling the homography estimation from representation learning provides better estimates, better homography estimates. And we also propose to use an additional photometric distortion step in the synthetic COCO dataset generation. And we hope that it could be used in the future, in future works, as a new evaluation benchmark of robust homography estimation. And then we presented a study of modern homography estimation baselines, 4 of them, along with the study of our bidirectional implicit homography estimation loss on both datasets SCOCO and PDS-COCO. And finally, our BiHomi loss achieves a new state-of-the-art performance for unsupervised homography estimation, which is also comparable or better than supervised approaches. And so thank you all for watching.
Thanks, Daniel, for the talk. We are running quite late, so we'll just jump to the next presentation. If anyone has questions, please just ask them on chat, and Daniel can address them directly. The next talk is by Ufuk. Are you around?
Yep, I'm here.
Good. So it's a workshop paper called DFM, a performance baseline for deep feature matching. It does something very simple that works very well, and I found it very interesting, so I hope you all find it as interesting as I did. Okay, the floor is yours.
Oh, can you see my screen?
Yes, it works fine. Thank you.
Okay. Hi, my name is Ufuk Efe. I'm a senior Master of Science student at Middle East Technical University. In this presentation, I will talk about our work, DFM, a performance baseline for deep feature matching, in collaboration with Dr. Kutalmış Gökalpince and Professor Aydan Alatan. This work was performed in a joint research project between METU Center for Image Analysis and Roketsan. Classical image matching pipeline consists of feature detection, description, matching, and geometric transformation estimation steps. Most of the popular algorithms before the deep learning era have focused on one or more phases in this pipeline. Also, during recent years, image matching met deep learning and a number of valuable efforts have been made. However, most of these algorithms still rely on the classical pipeline. On the other hand, some recently developed integrated approaches find correspondences between 2 images by benefiting deep features of a single network instead of separately doing feature detection, description, and matching. These integrated end-to-end approaches aim to output high-quality matches between images. And CNET and patch-to-peaks are some examples of integrated approach. Also, our algorithm DFM takes part in these approaches. Our key motivation was combining pre-trained deep feature extractors with a mutual nearest neighbor search algorithm. For a while, off-the-shelf deep feature extractors work very well on various computer vision tasks, and a simple but effective feature matching technique, namely mutual nearest neighbor search with ratio test, has been using for many years. We wanted to benefit from the pyramidal structure of the extractor by employing nearest neighbor search in a hierarchical way. Considering that this pyramidal structure has different semantic and local information in each layer, we believe that utilizing this information may be well for the image matching problem, since a good image matcher should output robust and well-localized matches. Given an image pair A and B, we first perform deep feature extraction for both images using a pre-trained VGG19 network. Then we continue with dense nearest neighbor search and hierarchy refinement steps. We utilize the DNSS block, which is basically mutual nearest neighbor search with ratio test, to find the matches between two feature maps at the lowest resolution. These are our initial matches. These initial matches correspond to matching areas in the previous layers. On the left, you can see matches at layer 5, and on the right, you can see corresponding matching areas at layer 4. For VGG19, matching areas are basically 2x2 regions. Then we feed the DNSS block independently with feature vectors inside these matching areas. By doing so, we restrict the search area and avoid looking for matches at irrelevant locations. Therefore, DNSS is enforced to match 4 descendants of 2 relevant matching areas. We apply this procedure to each matching area, and this kind of approach provides some beautiful properties. This figure illustrates that the first iteration of the hierarchy refinement algorithm, inherently a match in previous layer is expected to be better localized due to the fact that shallow layers have better localization. Here you can see an example of better localized match. Besides, thanks to the ratio test, a match may be discarded if its descendants are not discriminative enough. Here you can see the yellow match is discarded since any of its descendants find pair in relevant matching area. Moreover, if 2 or more descendants in a matching area find their partners, then a match in the previous layer is propagated. The purple match is an example of this, since it propagated as 2 candidates. Also note that it is also possible the number of propagated candidates as 3 or 4. DFM continues hierarchy refinement until the first layer. Our hierarchy refinement algorithm has some key outcomes. First, it gives accurate matches. Due to the pyramidal structure of the network, shallow layers are better localized, and moving forward, the very first layer provides accurate matches. Also, it gives robust matches. It is due to the consecutive application of DNSS. That means only matches who pass several tests can survive. Otherwise, they are discarded. And note that in each test, hierarchy refinement uses different descriptors. Apart from the high quality matches, DFM gives a great number of matches because our DNSS block allows propagation. Additionally, we can implement hierarchy refinement in a parallel way for each matching area. We should only execute iterations between layers in a serial way. Here we have visually illustrated the hierarchy refinement algorithm. You can see how matched features propagate as moving forward to the first layer. It started with 2000 matched features and scored 0.33 in terms of matching accuracy under 5 pixel threshold. And ultimately, it ended up with 9000 matched features with 0.92 accuracy. Also here, you can see that how the hierarchy refinement deals with outliers that are coming from DNSS at the last layer. Starting with such an outlier set that consists of poorly localized or complete failure matches, our algorithm is still able to find good matches, either discarding the outliers or enhancing their localizations. Even if it starts with 0 accuracy, DFM accomplished the task with 0.9 accuracy. And besides, it increased the number of matched features. Until now, I have talked about dense nearest neighbor search and hierarchy refinement, which we have named this structure as stage 1. Also, we have realized that although stage 1 successfully worked for many image pairs, it suffers under extreme viewpoint changes, more specifically under significant inline rotations. Therefore, we have added a preliminary step, namely stage 0. In this stage, DFM basically performs a coarse transformation estimation using matches that come from only terminal layers. which have better semantic information. And hence, these features are robust to an extreme viewpoint change. Also, utilizing this coarse homography, DFM warps the second image and roughly aligns it with the first image. Then we feed our stage 1 with image A and the warped version of image B. We have observed that this kind of approach improves the results, although it is not strictly necessary. And now let's see the results. You can see on the figure feature matching evaluation on H patches dataset in terms of mean matching accuracy, and variants of DFM are demonstrated as dashed lines. DFM achieved a better performance than the state of the art for lower pixel thresholds. Apart from the promising matching results, also DFM has much more matches than other compared algorithms. This means DFM returns denser matches, and claiming that there are at least these many matches giving these MMA results. The qualitative illustrations show that DFM is able to find denser matches. Also, DFM can provide further denser matches by arranging the ratio test parameters, but it may also create some outliers. We have adjusted the parameters experimentally. Performing a grid search for optimizing the parameters is one of our feature plans. Also here you can see DFM still has an acceptable performance even in the presence of significant viewpoint changes between images, and it finds denser matches. Thanks to our rough alignment at stage 0, DFM is resistant to some level of inline rotations. You can see single stage DFM's results at the bottom left. And obviously it is worse than the two-stage approach, which can be seen at the bottom right. Note that patch to pix has no alignment step. And if we apply our stage 0 as a preliminary step before it, patch to pix may also perform well under some amount of inline rotations. We also leave as a feature work applying our stage 0 to other algorithms as a preliminary step. As a summary, our main contribution is threefold. First, we have presented a baseline architecture using only off-the-shelf deep feature extractors with no training and only employing standard techniques. Second, we have shown the strength of mutual nearest neighbor search with ratio test when utilized for immediate descendants in a hierarchical way. Finally, we have also shown the performance improvement of rough alignment with semantic layers as a preliminary step. In other words, our stage 0. After all, DFM obviously has a limitation, which is the initial warping assumes that the match scenes are planar. So in non-planar scenes, stage 0 will quite likely fail. Frankly, we didn't evaluate DFM on non-planar datasets yet, like InLog and Ahun Day Night. Thank you for listening. I will be happy to answer any questions you may have. Also, our code will be publicly available in a few days, and feel free to contact me. Also, I will be on the YouTube chat to answer questions. Thank you.
Thank you. So I guess for questions, do please ask them into either the YouTube chat or the Zoom chat we have right now. Okay. For the sake of time, we'll skip the question sessions until we buy more time. I think we're running a little bit late for the schedule. Sorry about that. Okay. So we'll go on and to the next part of the workshop, which, let me just bring my screen up. Not this desktop, but the other desktop, which is a challenge presentation. So what we'll do now is that we'll, okay, if I get the keyboard to work. I'll briefly go over what we're going to show for this year's challenge. So this year, we had some changes to the challenge, as well as new data sets, and also some new interesting synthetic challenge introduced as well. So we'll go over them and also discuss some of the results, including the winners here. So before we begin, for those of you who were already here for last year's challenge, might have already are already well aware of the benchmark, but let me just introduce it quickly again so that we're all on the same page. So basically, what we're interested in our work on this benchmark and challenge and everything is answer to this simple question. So we are really interested in how good is a method that you want to evaluate for image matching is good in practice. So as Eduard briefly mentioned this at the beginning of our workshop, there are many, many methods out there that are aiming to make this happen. And what we did was to go a little bit beyond what was available with the focus on these three main points. So the three main points being using downstream metrics that are more close to what we're expected to get in practice. For example, before we relied a lot on some things like repeatability, matching scores, etc. While they give a good idea of how good things are, they're really not exactly showing how they work when you put them into a SLAM system or put them into structure from motion reconstruction and so forth. So that's what we're trying to evaluate with. And we wanted also to be able to evaluate with as many appearance changes in the data set as possible, not just synthetic ones, but also viewpoint changes and 3D perspective changes that occur according to those, and also illumination, seasonal changes, and so on and so forth. And this requires us to have a large scale data set, which did incur some issues when we were trying to get the ground truth out of it, because getting 3D ground truth is not going to be trivial if we do it in a massive scale. So here's our benchmark pipeline. What we have here is a modular pipeline that tries to implement the image matching scenario, either stereo or multi-view, and try to compare that with some ground truth, stereo, or SFM results that we have available from our data sets. And the important thing here is perhaps the ground truth itself is non-trivial to get for large scale. So we take advantage of the fact that if you have thousands of images, registering them actually is possible up to quite an accurate degree, even with existing methods, because a lot of images have high overlaps and they create a very nice way of verifying each matches and so on and so forth. So with that, many images reconstructed data set, we can then try to do a subset of those images and pairs, which make a harder problem to solve. And then that's how we evaluate various methods here. Well, that actually used to be the case, at least for 2020. But now with 2021, we have more data sets that do not actually obey this, and some other pipelines could be used, and even some synthetic data sets where we know for sure what the exact ground truths are in terms of geometry that created the scene. We'll see about that later, I guess in a few 10 minutes. And again, I want to emphasize this once more. We are evaluating using what happens downstream, not by some metric that is showing some proxy performance of local features or matching strategies. And I believe this is very important for pushing further, because as you saw before, some of these proxy metrics might actually provide you some misleading ideas on what is actually working and what is not. So hopefully by doing this task-based evaluation, we get around that sort of a potentially overfitting issue. So once we have this benchmark, I want to talk a little bit about how you actually submit your method or evaluate your method with this benchmark framework, which is already open source. you could easily do that by just providing some local features or feature matches and all that. And what this benchmark program will do is just do the standard pipeline for you for all the rest and all the rest of the pipeline. For example, matching, outlier filtering, ransack, or even running CoolMap. This framework that we have will do it for you so that you don't have to worry about it. If you're a local feature person, you can actually just focus on the feature part and then evaluate the entire pipeline task performance without having too much of an implementation issue here. Or if you are also wanting to provide some custom matches, it seems like that's very important from our earlier editions. You could do that as well, or you could skip the entire ransack and traditional pipeline and do something yourself on the outlier filtering as well, which is also an option that you could do. And once you provide those results, you can actually try to now evaluate your method's performance in terms of downstream metrics. And one of those are the mean average accuracy. So this is the average ratio of correct estimates in terms of your pose of the camera using various degrees of thresholds for determining correctness. So that will be up to 10 degrees for mean average accuracy at 10 degrees. So we consider the rotation translation errors and we take the maximum just so that we have a single number that we could have a look at. And we could do this for both stereo and multi-view, and we can also take the average between different tasks. And because this is not just, one metric is not just good enough, we also provide views into some traditional metrics, like if you're interested in repeatability or matching score, we can also provide them as well. And also for multi-view, like SFM scenarios, other metrics like number of matching images, number of landmarks, or track length are all available here, and also the average trajectory error. And but in our case, at least the challenge, we use the mean average accuracy for also the multi-view case so that we could have one metric that gives an idea of how a method performs both in stereo and multi-view scenarios. And that's what we use for actually ranking the methods as of now. So now, how do you actually use this? So one of the things that you probably want to do before submitting is validation. And you could use the benchmark repository and clone it and try to use your own method locally to see what is actually the optimal parameters, should you set this up so that the submission actually works, and all that is possible within that repository. And if you are interested in certain local features or methods that are out there, there's a lot of baselines that are already ready in not only OpenCV, but also in our image mention baselines repository, which you can easily use and have a look at when you develop your own method as well, because this will give you an easy way of integrating later your method into the baseline. And I want to also mention that we use robust matchers, not only ransack, but also other things like dgensack or usack and all those things. And importantly, those ransack methods and our discovery has now been integrated into OpenCV 4.5 thanks to Dmytro. You can actually look at this post here that talks about it in more detail. And since this benchmark is designed for a massive deployment and massive evaluation, massive scale, running a single method might be doable on your laptop, but not probably hundreds of methods which we had to do for this challenge. And to do that, if you have a Slurm cluster around, this benchmark nicely integrates with that as well. So this is how it looks. You basically set, once you have those repositories cloned and everything ready, and you get the matches extracted, you need to create a configuration file, which is a JSON file that encodes all the important details and how you should run, for example, would you run ransack, would you run dgensack, all those things go in here. And once that JSON is ready, then all you need to do is designate that JSON file and the benchmark will run for you. And now you know how to run the benchmark. You might want to submit to the challenge. Submitting the challenge requires you to obtain a password from us. We have a password protected upload server for obvious reasons. And you need to provide your configuration, features, and also maybe matches into a single zip file. And we will then use that zip file to validate, run things, and return those results on the leaderboard. One important thing that changed this year is that we also provide a validation script to validate your submissions. We had too many submissions that had some minor issues that needed to be tweaked to be automated. So we created a validation script that runs also on our servers. So if you don't pass your validation locally, you'll basically, when you submit your package, you'll just get an email very soon saying that something is invalid with the details on what's invalid. So you should validate your submissions with the validation script before you submit it. And for more details on the submission rules, please see our submission webpage. We will keep this open even after the challenge. So our hope is that people can use this leaderboard as a guideline of trying to see which method to use. And yeah, and finally, Dmytro has written a nice tutorial on how to actually create submissions, how it goes even in more in depth into showing an example of how ransack or matching should be tuned on the validation set and how to run the validation script. So do have a look at this before you do any submissions to our challenge as well. And finally, I think this is something that's very important that I want to give a shout out. This is actually from Dmytro. And is that please don't use default ransack. We have much better methods that are out there in that right these days. So do you, and it's even integrated in OpenCV, so I don't think you have any excuse anymore. So do use the proper options when you do evaluations for these poses and everything, since, well, they change the story by quite a lot. Okay, so that's a quick introduction of the benchmark. And again, probably for those of you who were here before in last year's edition, may be not too much new, but the takeaway really is that you want to use the validator now and also some better ransack. And I'll now hand it over to Eduard, who will talk a little bit more about the data sets that we have added.
1, 2, 3. Can you hear me well now? Do I have an echo?
Wow, there's a very strong echo.
1 second.
Your echo was large enough to throw the automatic transcription software off. So
now, same.
Oh, can you
now
say
it's better,
more?
I guess.
Okay, I can just do it without headphones. How about now?
Yeah, that's okay now.
Okay, then you can read yourself. Okay, I'll try to go over this pretty quickly. Can you see my screen? Good. So I'm going to talk a little bit about two of the data sets. One is the PhotoTourism dataset. This is the dataset that we used in 2019, in 2020, and again in 2021. So you have seen it before. It's a dataset that is generated from publicly available PhotoTourism data. As Kwang said earlier, the idea is to do a reconstruction with as many images as possible with a good SFM framework. and then subsample these images to make the problem harder, more difficult, and then use that for evaluation, right? With the ground truth that we get with all of the images. And the important thing is that if you use PhotoTourism data, you can actually register images like these in a 3D model. These are images that are actually used in one of the validation sets that we publish, or the training sets. You can use them for training from the Fontana di Trevi. And you see how you can have images with Instagram filters, with drastic illumination changes, with big scale and viewpoint changes, and you can still register this correctly. And this is crucial, especially if you train models, if you learn, apply any ML, because if you don't have this in your training data, your algorithm is not going to be robust to these transformations. And also for evaluation, because otherwise it's biased to simple transformations, right? So we provide training data that was already available, but we reformatted it. We have about 25,000 registered images, so you can use whatever you want for this challenge, as long as the scenes themselves, not only the images, but the scenes themselves don't overlap with our test set, which has 9 different scenes with about 4,000 images in total. And well, this is an example of the kind of reconstruction that you can get if you throw enough images into an off-the-shelf SFM framework such as Comma. We got some complaints early on about, can you call this ground truth? In the end, is an SFM reconstruction, right? It's not perfect. Okay, let's call it a pseudo ground truth. But we still think that it's pretty good. We made a test that you can check on the paper if you are interested, where we reconstructed one scene while adding images to it. So you take 100 images, you take 200 images, you take 400 images, 800, and all, which was about a bit more than 1,000. And then measure the quality of pairwise poses, right, on the common set. And as you see, the numbers don't change so much. So as long as you start using a relatively large number of images, they converge to values that are like below 1 degree, which is, I think, perfectly acceptable for the kinds of errors that you get in the benchmark itself, right? And we also got some questions about, are you biased towards the algorithms that you use to reconstruct these scenes, which is basically Comma running SIFT, I think it's root SIFT features. And it really doesn't matter, because while the reconstructions with different features can look very different, you see some examples here, reconstructing Sakrika with SIFT, with Superpoint and R22. The poses that you get using different algorithms are very simple, very similar. So that's not really a big difference. And ultimately, what we want is good poses, right? So as long as you can reconstruct it, and again, the key is throw enough images into SFM so that you can get a good model. As long as you can do this and the poses are good, you can use this for evaluation. If you are curious, we have many more results in the paper that we published in IGCV last year, so please feel free to consult it. This year, we added 2 new datasets. One was the GoogleUrban dataset, and the other the PragueParks dataset. I'll tell you a little bit about the first one. The GoogleUrban dataset is about 1,500 images that are collected from video sequences captured with the phone. These are used internally at Google for evaluation purposes mostly. And one thing that is different from the other 2 datasets is that these don't come from an SFM model. So we don't use them for reconstruction. What we do is we register these images against maps that we already have. And that causes some differences in the evaluation that I'll talk about in the next slide, I think. But if you look at the images, on the right, you have an animation of some examples from Tokyo. They are mostly on facades, on urban areas. They are pretty close up. And they are very different from the PhotoTourism dataset in that they are not focused on one central landmark, right? Like the Trevi fountain that you saw earlier. And that means that they are, in some ways, easier and in some ways much more difficult, because especially since the phone is held in portrait mode, there can be very little overlap between one image and another. We blur faces and license plates automatically and double check by manual inspection. But even so, releasing data from industry is always a bit difficult for a number of reasons. So we released this data set with a restricted license. We made it publicly available only for the duration of the challenge. So if you used it, please be aware that according to the license that you agreed to, it should be deleted by tomorrow. But we can not capture, but release similar images next year if we want to. That should not be a problem. So we may reuse these images. We may use images from different scenes. One very nice thing is that we have data from many cities across 4 continents, which is something that we didn't have with the PhotoTourism dataset. We actually did have data from rather different locations, but when we chose the validation and the test split, it so happens that by random chance, all of the test sequences were in Europe, which is a pity. So now we have Tokyo, we have Bangkok, we have Singapore, we have Australia, we have Canada. You know, it's a little bit of everything, South America too. So that's good. It's a bit less biased in that sense. And the data itself has exhibits many different types of transformations, such as illumination changes on the 2 top right images, lots of occlusions. That is on the bottom right, on the second from the right, you see that the scene is occluded by 2 cars, and it can be quite difficult. And this is something that we see in the numbers. So I took as an example one of the top performers. And if you see, you can compare the numbers for stereo, and it's 0.64, 0.81, and it drops to 0.44 for GoogleUrban. And for multi-view, it's at 0.79, 0.50, and 0.38. And one thing that is interesting is that, contrary to the other 2 data sets, the multi-view, well, that's not true for PragueParks as well. The multi-view task is more difficult than the stereo task, and that is because we don't ensure that the images overlap like all at the same time. That is not exactly what we do for the PhotoTourism dataset either, but it's closer to that. But it's more of a transitive property, right? A matches B, B matches C. So you know, A, B, C should be able to be matched if you throw them into a very good SFM model. But you still have a smaller overlap between individual pairs of images. So that explains why, in case you were curious by looking at the results. And now I'll pass the floor to Dmytro.
Thanks. Let me share my screen. I hope the Zoom now don't crash. Okay, so okay, present. Do you see the presentation? Yes, great. So the PragueParks dataset is done by me with help of one commercial software. And then I had 2 motivations to do this. First is to try to gather something which is not urban, maybe something with more nature, and maybe something with a different shift and distribution of the viewpoint changes. So as you can see here is this is like a wide camera trajectory, and this is a reconstruction done for some rocks and the vegetation I have like really close up, and another is like huge tree in one of PragueParks. So just captured with iPhone 11, just pretty good image quality, although not with night. So we skipped this idea for the probably next year now. And it was like super easy to reconstruct this with reality capture. This is commercial software by Czech company. and they granted us a license for doing this workshop. And the benefit over ColMap, and this is 100 times faster, so we don't need to use huge cluster or wait for a month per sequence as we did for the PhotoTourism. It just can be done in a couple of hours, and it's super nice. And the idea with the test data is like instead of having like real time 24 FPS, just use 1 FPS. And it's actually not just resampling that. It's a bit more complicated based on the key points visibility, and you can actually check it and run it yourself. So I have open sourced all the code, and you can use actually other software for the doing 3D reconstruction. And also, and PragueParks, as we will see in the results, turns out to be the easiest data set. So like next time I will do like more challenging data sets, and now it's actually easy to create new and new ones. So let's analyze the results. And so first, like for the rules, we have a bit of progression from the previous years. Originally, we have like several descriptor size categories, like small, like orb-like for binary descriptors, and regular, and then large. And okay, we had only submissions for that entries where we have a price, and it was like a regular standard thing. Then we actually say, okay, now we have a lot of papers which don't use key points or can use built on top of D2Net or whatever else. So, and we can lift this restriction on the descriptor side. However, we asked participant, then if they use a huge descriptors, they should match them themselves, because it's really, really computationally expensive operation for us to do it, and upload already matches. Also, it kind of someone could cheat. Actually, none of our participants cheated as far as we checked, and everything was okay. So I really love that. And by cheating, I mean one can use like 3D reconstruction and then submitting this as a matches, but everything was okay. And here are results. So I will first announce the winners, and then do some analysis, and then pass the presentation to actually then winners themselves with possible open discussion. So we had a bit less submissions than last year's, but like very comparable numbers. And this year we were super low on time, only a bit more than 1 month for submissions. That's because we were working on the data set. I was converting and fixing the pipeline for PragueParks. Eduard was getting all the permissions to publish the GoogleUrban, so we were a bit late, but still thank our participants to this like great participation. And actually, somehow in paper, probably in the last year, not that many papers are used our benchmark. It's funny that actually much more cited us as a like yet another benchmark, but most of them haven't used it. And that's actually a question we would like to discuss with you, like why is it the case? Is it too hard or it's not understandable how to submit or whatever else? And the like popular benchmark are IHAN and HPatches. Oh, okay, HPatches is super easy, and IHAN is probably also easier to run. Okay, we'll see. And the winners of our challenge are 2 teams. One is McV Research, who built a like nicely engineered pipeline. And runner-up is from Tencent, who also built actually quite simple in the ideas, but different in implementation pipeline. And what is the funny thing that for the 8K, the winner is McV, and the runner-up is Tencent, and for 2K is the other way around. So they basically two won the both categories, and the difference is actually quite marginal, which you will see. And we congratulate, and we'll send a prize a bit later. We'll contact person and discuss how to transfer the money. So let's go for analysis. First, stereo 8K category is that this, I split it, the results not as the way it's done in leaderboard, because in leaderboard we average based on ranks, and here it's averaged on the data sets per single category. So in the leaderboard on the website, we have rank for all 6 categories, which means 3 data sets and stereo and multi-view. Here is only stereo. And what's interesting first is this MEGV solution, which re-implemented superglue and combined disk and superpoint local features, fit into superglue, and also add a lot of post and pre-processing thing. The second is here is Lofter, which also would be talked about. And the most challenging thing was how to actually marry Lofter with our benchmark, because we expect key points, and without key points, the results are quite bad. So it's actually was quite an effort doing this. ReZ plus affine hardnet 8. This is a completely handcrafted detector and learned patch-based local features. And as you can see, it's not that bad performance-wise. And the rest are actually not using the custom matchers and including this ReZ, so you can see quite a difference. And probably the most thing is we were really worried about this additional work for creating dataset. Was it like futile or useful? And it turns out that actually GoogleUrban is the hardest and the most decisive thing. So if you are good there, you are probably super good. And the PragueParks is on the one hand is a little bit easier for the top methods, but as you can see for the SIFT performance and this tutorial thing, so the only difference between this tutorial and the ReZ is a detector. And the most difference are if you go for the PhotoTourism, you see this red line is almost the same for these two things, but for PragueParks and for GoogleUrban, the difference is huge, and probably that on this natural and like urban style thing, you don't have that many good blobs, but much more corners, which are also used by Superpoint. For the multi-view, the results are similar. However, the overall difference is much smaller, and if you have enough images, it probably doesn't really matter for you to have a good features, as we had seen before when we generated the ground truth for PhotoTourism. So, but if you do stereo, it really matters. For 2K category, there's like much more submissions in this category, and one of them was E2E, and this is actually a vanilla superpoint plus superglue with minimal tuning with off-the-shelf GitHub models, and you can see that there is a difference between it and winning entries, but this is not that huge. So like vanilla superpoint and superglue is the way to go. We also have this Kotter and context desk. And what also interesting is that disk, it looks that it performs very well, or not very, but just well on GoogleUrban, good on PhotoTourism, and not that well on the PragueParks. And as you can see, this blue one is not even visible. And maybe that's because the mega depth is actually similar to our PhotoTourism data, and it's just overfit there. This is another kind of lesson to learn, that one might need to have more diverse data. And with this, I'm going to almost conclude. Again, here for multi-view, almost no difference whatever you use. It's just fine. except that, okay, for 2K or Sift is no way to go, especially on GoogleUrban. It's just terrible performance, which I am very happy with because, okay, I love Sift, but we need to move on, right? And actually, since the previous year was basically with introduction and these benchmarks of Ransack, and the people just used our recommendation, and I think no one played with different Ransacks besides the peak and threshold for the Gensack. It's kind of now the field standard for the two-view matching without non-collaboration. And thank you. And I think Vassileios now will follow with SimLocMatch.
Hey, while Vassileios has prepares for presenting the SimLoc thing, I found it also quite curious that many of the top entries also utilize semantic segmentation quite a lot. Maybe that's gonna be something very important as well. Okay, you're on stage, Vassileios.
Am I back? Zoom
Yeah.
was frozen for a bit. Okay. And do you
Yep.
see my screen too?
Yes.
Okay, great. Yeah, so another thing we wanted to do for this year is to add a second challenge, and the idea was to add a simulated database challenge, synthetic, basically images. And there are a few reasons for that, but for me, the best reason is that it nicely complements all the other data sets that are in the other challenge. And I'll go into a bit more details about specifically the motivation. So as we start basically describing the motivation, the first question is, why do we need synthetic data sets? And there are a few key reasons for that. First of all is to precisely control variation factors like which lights are turned on and off, the sun position, the occlusions that we see in the scenes. Then a second very important case is to have pixel perfect accuracy of ground truth, which is not available in most of the other cases, because when you're building something automatically, then you're not sure about every arbitrary pixel in all the images. I think Kwang mentioned before something about possibly some people complained, I think in their paper, about biases. Well, this could be one way to mitigate that, right? Because then no one can claim that then you have bias due to call map or Sift or how you build your ground truth. And the last and a pretty big one actually is privacy, that you don't need to go out and collect data anymore. You don't need to crawl random images from Flickr and get into possibly some interesting violations there with respect to faces or GDPR stuff that are pretty important overall. Obviously, there are a few potential drawbacks. For me, the biggest one is the simulation versus reality gap. But this could be turned around, right? And instead of an issue, we could actually see it as an opportunity, and we can see it as maybe a way to facilitate research on how to close the domain gap between real and synthetic data in our field too, which honestly has been quite interesting and already happening for a few years, especially in the robotics community, but not that much in our case. So just again, some basic differences between having a pseudo ground truth, for example, using call map, and having a model-based ground truth, is that as also Kwang and Dmytro described before, then pose is something that is used quite a bit in the evaluation when you have pseudo ground truth, because this is the most accurate tool you might have. Also, obviously, we could also argue that it's important to have, not only due to the fact that it's the most stronger tool, but it's also the most. But on the other hand, we don't have the actual data to get into these discussions when we don't have pixel level ground truth. So I know that there's been some kind of other side of this whole story, which is the localization workshops and the localization tasks, which also rely quite a bit on poses. So the idea is instead of having to rely on poses, then if we could somehow rely on pixels too. Again, we haven't completely answered if it makes sense or not, or if it actually is important to use pixels instead of poses. But again, this will be something pretty interesting to facilitate with the synthetic data. So just two cases, I think both were mentioned from one from Marc before and one from Kwang and Eduard, is the two standard benchmarks that use the call map based approach. SFM was obviously the IMC one, and Johannes' paper from I think it was the same year as AIDS patches, if I remember correctly. So on the other hand, there's some cases where we can claim, again, it's not exactly ground truth, but we can claim that it's very close to actual ground truth. One of them is AIDS patches, because the poses were evaluated, the homographies actually were evaluated using manual clicks, and a lot of them, and a lot of human annotation. So we don't expect any huge errors there. And the interesting thing is that when you have homographies, then you can be sure about every pixel as long as it's inside the visibility masks. So again, there's no blank spots with respect to the model and having results about arbitrary pixels. So another case that we want to show here is that we can use actual ground truth coming from 3D models and making a benchmark out of images rendered from these 3D models. Another motivation, again, it's not very obvious that this is a big problem now, because most of the methods we see have lots and lots of key points, possibly thousands. But the more we go towards fewer key points in the future, the more important this will become. Is that, as you can see here, this comes from the image matching challenge evaluation leaderboard. There will be some cases where we're not sure about specific depth estimates, right? So this will always be the case, and we cannot avoid that when we rely on structure for motion methods. And this is not relevant for the pose, as long as we have good enough, a lot of good enough pairs, but still, this is, as I said, something very important, possibly for the future when we want to focus on fewer and fewer key points. And what we want to avoid is a situation where every paper reports different rankings and different results. We want to avoid basically something similar for the benchmarking case, like every benchmark, due to the fact that they possibly have, let's say, not full information reporting different rankings. Another use case that is very important is SFM-based methods will not be suitable when we want to go indoors. I mean, they work, but it's not as good, because as we all know, SFM has a huge problem with textureless or not interesting enough surfaces. So that would be another good use case. I've cropped a few areas here where this would be a huge problem, like floors, stairs, that they all look the same. So this will be traditionally challenging for an SFM-based pseudo ground truth. So the goal of having then simulated data, synthetic data to evaluate matching is to use these 3D models to build large-scale benchmarks, both for matching and visual localization. So we started, again, this dry run, if we can call it, with 7 scenes and 80K image pairs. We will present more information about the whole data set and release it later on this year, possibly together with a technical report. And here's a discussion about the future roadmap as we see it. The plan is, as I said, to release it by the end of the year with a few scenes, add some pure detection relative pose estimation tasks, add the validation set, introduce more metrics, more tasks. We heard the very interesting in the very interesting talk by Marc about line matching. So these are things that we could definitely include, since we have the ground truth 3D models and we know all the primitives in there. On a separate but related note, we're also looking into how to use this for localization, which obviously includes a heavy aspect of local descriptors and image matching. And more interestingly, we're hoping to release a joint dataset that has some scenes in both cases so that people can test how one affects the other, which will be a nice research question. So going back, I think Eduard described his point of view about why starting this workshop. For me, one of the key things we discussed, and I was very keen early on, is to basically go to this green sentence there, which is if we can dump as soon as possible key points and descriptors. So I think the first year we were a bit disappointed because all the methods were pretty much traditional, but it's looking more and more likely that we're getting close to the place that they won't be as relevant anymore, especially for the very interesting and difficult use cases quite soon. So this is a good thing for me. On the other hand, we want to go even deeper, right? And go even more difficult cases. So someone might only have a method with 8 key points or something. This is the extreme case, obviously. We want to be able to be sure about every point in the image, and this is a way to do it, having this kind of benchmarks. Again, we want to go to higher level primitives like lines or planes. This will be a very interesting use case for the future. And also we want to utilize more semantics and geometry. I think a few winners in the PhotoTourism, I think, challenge, the dataset, they use quite heavily filtering using semantics. So again, having absolute ground truth for every item in the image will be pretty interesting. And yes, after this kind of small discussion, I think you should expect more later this year, including the localization scenarios and more information about new tasks for matching. And I'm quite pleased because we had quite a few submissions. Not all of them are public because we enabled the option for people to not publish their submissions. So we had 43 different submissions that were made public, I think from 10 different teams, if I remember, that chose to make them public. So I consider this a pretty good first dry run, given the fact that we only had 1 month, if I remember. And we discussed quite a bit about how to do the final rankings, but we decided not to complicate too much for this first version. So we basically did a ranking based on the matching success rate, which is simply if you get a match randomly, then what is the probability of it being correct? We're focusing now on adding things like false positives, but we haven't actually put them together in one single metric. This will happen later this year. So with respect to the actual winners in the end, so these are the 3 top ranking methods. So basically, again, I think exactly the same kind of pipeline from Megvi, from Xiaopeng and others is in the first place with quite high matching score. Runner-up is from Jiangming and others in the Zhejiang University and Sensime Research. And also the 3rd place, which originally we also wanted to be part of the winners, but unfortunately we can't because Dmytro is part of this. So per the rules, we're not giving prizes. Is the Heritage Class Star, a bunch of different methods that were submitted by Fabio and Dmytro that were all quite good. So yeah, again, congratulations to all the winners. And I'm going to briefly discuss a couple of things that we learned. It's pretty interesting that negative results do seem to matter, at least for some cases. One great example is D2Net, which again, Marc before mentioned how well it can match day and night. But what we found is that basically D2Net is almost indistinguishable with respect to positive and negative pairs. So it basically finds the same amount of matches, even if you give it a negative pair. So this is pretty tricky when you want to do SFM. I think quite a few people identified that when they went on to use D2Net for an actual SFM building. And another interesting thing I personally liked from the things we learned there is that transformer-based methods, like the very recent, the very state-of-the-art methods, were actually obviously much better than SIFT. But the gains that we got with respect to, for example, the pipeline that Dmytro and Fabio put together, which is a bunch of mixed, I would say, not very modern, but also not very kind of old school like SIFT. So it has some parts that are not learned, some parts that are learned. And what you can see is basically going from this kind of mixed pipeline, from SIFT to this kind of mixed pipeline, you get a huge increase. But then going to a transformer kind pipeline, which everything is basically everything is learned, and it does not rely on things like Harris key points anymore. You get a much smaller improvement. So this is pretty interesting. And again, this shows that we probably still have quite a few space to go with respect to getting similar increases, like a 25 or a 30% increase in matching rates with respect to a pipeline that we know works quite well, like the Harris pipeline using Adalam and hardnet descriptors. And this is, again, to show the distribution of matching score versus the ratio of correct versus non-correct matches with respect to negative and positive pairs. And there's this is where you would see GTNet being all the way to the right, which basically means that it's pretty similar in terms of the number that it gives back, number of matches it gives back between positive and negative pairs. We have some other cases where they're more reasonable, and most of the methods are somewhere in between 30 to 50% with respect to how many true positives and how many false positives matches they give on average. There are some other interesting things that we can get from this benchmark. Again, we're planning to write something up pretty soon about all the things we learned, so stay tuned about that. And yeah, again, congratulations to the winners, and thank you to everyone that submitted and made this success, although it was quite new, and obviously a first version of more to come soon. So yes, thanks. And if there are no questions, back to Eduard.
Yes. Can you see me now? Can you hear me?
Yeah, it works.
Okay, good. So let me just present something quickly. All right. Can you see the slides now?
Yep.
Good. So we thought that it would be nice, since the challenge is, on its third year at least, for the image matching challenge, and also because SimLoc is very new, to have an open discussion. We are running like 45 minutes late, and I think the virtual format is not really very friendly to this kind of discussion anyway. So we had the open session or the coffee alternative, and in the end we will have neither of them. Let me just go over this very quickly. We'll upload the slides later. I just wanted to say that one thing that we wanted to do this year is to move the challenge to Kaggle. We talked with them, it did not happen. It would be very nice because it opens up a lot of doors. In addition to the visibility that it gives you, it makes a lot of questions irrelevant, such as, do we need different categories? Do we need to worry about descriptor size? Do we need to do this and that? Because you can have notebook-based submissions. You just submit code, it runs in a fixed budget, and then you get what you get. Now, that's the compromise, right? We will investigate it next year. It may or may not happen, because in addition to time constraints, there are certain difficulties in combining the benchmark that we have with this approach. We are aware that it will have difficulties in running, especially the image matching challenge. So, just running it on your own for validation is difficult. Submitting can create errors. And also other questions more general, such as, does it make sense to have other tasks? Do we have too many data sets now? Are all of them interesting? I think, as I said, let's not try to have a discussion about this now. But if you have feedback for us, please email us, because we are very welcoming to your questions, and we would very much like to address them. I think Vassileios had some points in here. I don't know if there is anything that you want to discuss.
Yeah, no, but I think you covered most of them. So yeah, we can wait if someone can read the slides, and if they have any interesting thoughts, you can email us, I guess, about future editions.
Sounds good.
And
yes,
one more reminder is that for a participant or so anyone to download it GoogleUrban to delete it tomorrow.
Yes, please do that. So we'll jump straight to the challenge talks, not only challenge, but some papers that I think are very interesting. The first talk would be by Fabio Bellavia, along with Dmytro, actually. Fabio, are you around? He is in chat. Let's see if he can connect. Oh. We hear you and we see you. Perfect. You have the floor.
So this one is the classic pipeline we use with Dmytro for the submission. It's a hybrid pipeline with some depth modules and some undercraft one. So
sorry, Fabio, can you make it full screen maybe?
Sorry, there is no full screen.
Oh, I just see the I think it's PowerPoint. It's fine.
Okay. And so let's start with the first module, that is the key point extractor. This is done by RSZ Plus. This is an extension of the RSZ that was made about 10 years ago by me. And RSZ was a multi-scale series corner detection, but differently from other key point detectors, is based also on edge mask, on a rough edge mask that drive the selection of the key points. And this mask is also used to enhance the derivative in the formulation of the ReRe function, that is the determinant and the trace. And in the end, it just combine a lot of maps by using the mean values to select on the map, on the image, to select point or not. And with respect to the standard point structures, except SARF, it increases the kernel dimension instead of downscaled image. So it try to improve the location accuracy. With respect to this RSZ Plus, just extract more key points, because from 10 years ago to until now, the descriptors, the deep descriptors accuracy is improved, and also the computational capability of the hardware. So we want to extract more key points, and we want to do this on finer scale, basically. And instead of using the scale and then the corners function, the corner function to rank the descriptors, we do here the reverse. And also for what I call the sub-pixel scales, that means scales where the differentiation scales is just lower than 1 pixel, we upsampled the image and then re-normalize it again to get more points. Also, we try to take the key points to be equally distributed, uniformly distributed among the image. And also the edge mask was improved a bit in the case of color image. Okay, here you can see the difference between the key point extracted with the standard RSZ Zeta and here with the RSZ Plus. So here there are the improvement when we test our new detector on the PhotoTourism validation sets, and on the main average accuracy, there is a gain about 10% in the 2000 key point competition, while in the 8000 is about 6%. Here there are the different improvements with respect to the letters. Now, for the next step of the pipeline, we use AFNet for patch normalization and HardNet 8 for descriptor. And These modules were implemented in Cornell and they are done mainly by Dmytro, of course. And then for the last part of the pipeline, we use a handcrafted keypoint matching. Most of the modules are already known, except for the blob matching to the Delaunay triangulation matching that you can find in this preprint here. So what is blob matching is just a framework where I take a bunch of matching strategies relying on descriptor and not or geometry, and I generalize in a single working plan. So there is a row-wise and column-wise. You consider the distance table to take only the m best one matches and intersect or doing the intersection of the union of these row and columns. We also, I also try to what happens when instead of the common nearest neighbor one-to-one match, we use a many-to-many matches strategies. And also when I use or not the F gene, that is the first geometric inconsistency nearest neighbor. But also because usually nearest neighbor ratio can be different if you use the first image as a reference on the second one. There can be other strategies for this that are here. What I did is simply test for different parameters the best situation on this dataset here for that includes planar images and also non-planar one. And the result is that the best configuration was this here, where for row-wise, column-wise match selection, I take only the 10 best one. I combine with the union. For many-to-many greedy strategy, I limit to 5 matches that share common key points. For the F gene, the standard one that is faster than this one is that was done by Dmytro, worked really good. And about merging with respect to the reference image, the different nearest neighbor ratio one can obtain. This one, the symmetric nearest neighbor, in this way, that is just the harmonic mean between the two symmetric nearest neighbor is usually provide the best solution. And doing this way, about I checked that about 5% in terms of mean average precision can be achieved on this dataset here. And this is for the blob matching. For the DTM, the Delaunay triangulation matching, it is a matching strategies based on geometry. It is a filter on the local neighbor. So how the name said, it works by considering the Delaunay triangulation one for each image because they are different. And a good thing about the Delaunay triangulation it's that I don't need to set a circle radius for saying which is a good a neighborhood or not of the image, because it's just the key point distribution that do this. And on this Delaunay triangulation, I define a neighborhood consistent with a key point or each other if the two key points are share an edge on the corresponding triangulation by when I transferred by the match from one image to another one. So how works the DTM? Just iterate. There are two main steps. The first one is iteration until the matches and the pruning stop. And what I do is mark the best match on the set of matches and remove all the inconsistent key points. Then I remove this match and repeat until the set is empty. Now I put again in the matching set all the marked, the good key points, and those that are consistent with any of them marked match. This is called the expansion of the triangulation. The first was called the contraction. And here you can see for the first iteration what happens. The green and the yellow are the good matches, while the pink and red are the bad, the wrong matches. And here also the retaining matches after this step, this iteration, are those in green and red. First iteration, second iteration, third iteration, and fourth and last iteration. You can see at every time the Delano triangulation is recomputed, that is changed, and always converge this kind of method, because we can only remove matches and not increase matches. And here there is the semi-visualization, but by highlighting the contracted matches and the expanded one for the first, second, third, and fourth iteration. And after this step, there is another one where I go backwards. I go among the iterated Delano triangulation, and I just put back a putative consistent match if there is, if for instance, a match fall inside this, on one image, the match fall inside this triangle, and when projecting on the other image, the corresponding points also falls inside the same mapped triangle, it is good. And here you can see the yellow are the matches included again, and so there is the final result. And blob matching più Delano triangulation matching, as also testified by the challenge, is good at providing a good recall. Maybe the precision is not so impressive, but also you have to consider that there are no distance involved, only relative position between the matches. So it is needed to filter with a model-based method. And as I said, the Delano triangulation matching is basically, there are no parameters to set. It's relatively easy to understand with respect to other graph match optimization used for this kind of application. And the check is always symmetric, and there is always a convergence. If you are interested in more result comparison with other similar strategies, with respect to the archived paper, there is this PDF here that include more updated evaluation. So that's all. If anyone have a question, or if you have time for questions.
Yeah, sorry, but for the sake of time, we'll move on to the next speaker immediately, which is Prune. And for any questions for Fabio, please ask them in the chat or send emails directly. And yeah, sorry, Fabio.
Don't worry, it's okay.
Okay, so Prune, I see that you have everything up. Stage is yours.
Do you see my screen?
Yes.
All right. Okay, so hi everyone, and thanks for having me. So I'm Prune, and I'm going to present our CDPR oral paper, Learning Accurate Dense Correspondences and When to Trust Them. This is a joint work with Martin Denelian, with Luc Van Gool and Radu Timofte, and we're all from the Computer Vision Lab of ETH Zurich. So in this work, we tackle the problem of dense correspondence estimation. So from a pair of reference and query images, we want to find the flow field relating each pixel of the reference to the query. And we visualize this by warping the query according to that flow. So as you can see here, dense flow estimation is prone to failing in case of occlusion. It can also be inaccurate, particularly in case of large appearance and viewpoint changes, and it is even ill-defined, particularly in textureless regions here, as in the sky. But the problem is that for lots of applications, such as pose estimation, it is actually required to have a set of highly accurate matches as input. So how can we know when and where to trust the estimated correspondences? So we propose probabilistic dense correspondence network, and together with the flow field, we infer a confidence map according to which the red regions are uncertain. So now let's look at the method. So most methods just predict a flow vector y at each location. Instead, our goal is to predict the conditional probability density of each flow vector y given the input images. So in practice, the network just predicts at each pixel location the parameters phi of this flow density. So how do we actually parameterize this flow density? From these empirical error distributions here, we see that errors can be categorized into two populations, inlayers and outliers. Current probabilistic method mostly rely on a Laplacian distribution. It has two parameters, the mean, which corresponds to the estimated flow vector, and the variance parameter. We instead use a constrained mixture of Laplacians. So it has m Laplace components. All components have the same mean, but different variance parameter. And each component is responsible for a different range of uncertainty that roughly corresponds to different regions in the error distribution. So compared to the single Laplace, the incentive of our approach is that it allows to predict for each match the probability of inlayer versus outlier that are each modeled by separate Laplace components. So now at each pixel location, the network predicts the mean and the uncertainty components, and so from those we can estimate a single confidence value. The second big question is how do we train? Because it's very difficult to obtain dense ground truth data, most methods rely on self-supervised data. So training images are basically generated with simple transformations like here. But on these transformations, the network learns to heavily rely on global smoothness priors and interpolation. But this strategy does not generalize well to real data. It leads to overly confident uncertainty predictions like here in the sky or in the field. Because ideally, we would like the confident estimation to exclude all of these areas. So we tackle the uncertainty generalization issue from the data and the network perspective. So first from the data, basically the major problem is that the synthetic flows are too predictable. So we just introduce some small perturbations in the flow that will break its global smoothness. In terms of architecture, the straightforward way to just predict all parameters of the distribution would be to increase the number of output channels of this flow decoder. But in this case, the network relies too much on neighboring information when predicting the uncertainty at a particular point. So instead, from the standard architecture, we build a parallel uncertainty decoder, and it inputs the correlation volume and processes the information at each point independently. So this was the result that I showed before, and with our approach, we have much better uncertainties. Another cool feature that is enabled by our uncertainty prediction is a two-stage refinement strategy. So if we start from this image pair, we can feed it to the network and we get a flow and an uncertainty. And then we can use the confident matches to infer a coarse homography with RenSac. Then the query is varped according to that coarse homography, and we get a new pair of image that is coarsely aligned. This new pair can then be fed into the network for a second forward pass, and we get a new flow. But the final flow relating the original images is just a composition of these two flows, and we see that it's much more accurate than the first forward pass flow. And it also has more confident regions. And so, for example, the pose estimation error of the first forward pass is 60, whereas of the two-stage alignment is 1.5. In the same spirit, we can replace also the first homography by a multi-scale approach. We obtain the PDCnet architecture by adding our uncertainty decoder in GlueNet GoCore, and we train our network using the negative log likelihood loss as the only objective on both self-supervised data and sparse ground truth data. Now let's look at the results. So here we first show qualitative results on scenes of megadepths. And so this is the VARP query according to PDCnet, and the unreliable regions are shown in red. To compare, we also train a non-probabilistic baseline, a GlueNet GoCore, on the same data. And here we see that our probabilistic approach allows to identify accurate from inaccurate regions, but here we also see that it improves the flow prediction itself compared to non-probabilistic baseline. In this other example, we see that PDCnet does very well in extreme appearance and viewpoint changes. Now, in terms of metrics, we evaluated PDCnet on multiple benchmarks. So we have Megadepth, Robert Carr, and ETH3D. And on all these data sets, it's better than the previous state-of-the-art RenSac flow and also the baseline GlueNet GoCore. We also looked at optical flow data at Kitty, And here, surprisingly, is better than Raft, even though we didn't train on any optical flow data. We also evaluated PDCnet for pose estimation on the YFCC 100M by using only the predicted confident matches. And here we see that PDCnet outperforms the previous dense state-of-the-art, as well as some standard sparse methods. With PDCnet, we can also do dense video construction. And so the first step here is to find dense confident matches. And here we see that we're applicable to large viewpoint changes. We then fed all of these confident matches to ColdMap, and this is the resulting point cloud of the Aachen city. So the first thing is, well, it's pretty dense. And then here you see that buildings are reconstructed with high quality. Finally, another application is texture transfer. And here it's quite obvious that we are applicable to extreme appearance variations. Finally, I would like to say a few words about our submission to the SimLocMatch challenge. So we computed the matches using the PDCnet multiscale, and we resized all images so that the smallest dimensions was 700 pixels. We then applied MaxSight to the estimated matches. And so these are our final results. So the first thing is we get quite a few inlayers, and the reason for that is that we get quite a few matches. So that's an example. And all of the confident matches are around 10,000K. So that's a lot. 10K, sorry. And the other observation is that we also get a relatively high number of matches for non-matching images. And the reason for that is that PDCnet finds locally matching regions, such as pavements here, even in majoritarily non-matching or failing images. And so since we're in a dense setting, this directly creates quite a few matches. But there are multiple ways we could improve the results, and the most important way is the data. Because, for example, PDCnet does pretty bad in these type of images, which have large 180 rotations, because they're not represented in the training data. And as I said before, the main challenge is also the lack of ground truth data. So one way to improve this would be to simulate such pairs with mirroring, for example. We could also use a real image in an unsupervised approach. And that's actually what we do in our latest work, VARP consistency for unsupervised learning of dense correspondences. That could easily be applied to PDCnet. Finally, there is still an open challenge on how to use dense matches in the sparse setting where we should provide a fixed set of key points. So that's the case of the IMZ challenge. Because imagine you have to match all of these images. You see that if you keep all of these key points, the number will very fast increase to a large number. So the straightforward way here would be to round to the closest integer, but then the matches are less accurate, and in a dense setting, that still is quite a few matches. So then the next thing is to lower the resolution, but the lower the resolution, then the less accurate the prediction is going to be, and also the largest the rounding error or the quantization error is going to be. So basically, one needs to find a trade-off between prediction resolution and accuracy of the matches. Of course, we could get some fancier approaches, like selecting key points that are the most used within the image sequence or tracking points. So that's still open challenge. So if you're interested, you can check our website for more visualization, and the code is also available. Thank you.
Awesome. As usual, please ask questions in the chat. Sometimes we might have time for a couple questions. So if you have any good questions you want us to relate to the speakers, do let us know. And I think our next presenter is Jiaming Sun from SenseTime here at Zhejiang University. Stage is yours, Jiaming.
Okay, thanks. So can you hear my can you see my screen?
Perfect. The video
Yeah,
shows up really
cool.
nicely as well.
Yeah, thank you. So yeah, hi. This is Jiaming Sun from SenseTime and Zhejiang University, and I'm here to present our work Lofter in this year's CVPR. And this is a joint work with Ze Hongshen, Yuan Wang, Hu Junbao, and Xiaowei Zhou. And as the organizer just mentioned, we have also submitted our entry to the IMC with Lofter, which I will talk a little bit about by the end of my my presentation. So the IMC submission is mainly made the effort by Xin Yihe and Yuan Wang. So yeah, let me just get started. Okay, So the standard pipeline for local feature matching can be separated to 3 phases, which is feature detection, description, and matching. And this pipeline has 2 major challenges. And the first challenge is that a feature detector may fail to extract enough key points that are repeatable between images due to various factors such as low texture, repetitive patterns, viewport or illumination changes, and motion blur. Like in this example, the key points on the edge of the table and in the shadows are not repeatable. So without repeatable key points, it's basically impossible to find correspondences, even you have a perfect set of descriptors. So another challenge is that the local descriptors are actually not position dependent, which means that although point A and B in the left-hand image are on the different locations on the image, the extracted local descriptors are similar, since there's no difference in the image appearances between the two regions on the white wall. So as a result, the similar descriptors can be potentially incorrectly matched, which will introduce error to the final post computation. So we propose our solution, Lofter, to tackle these 2 challenges. Lofter uses a detector-free pipeline to avoid the repeatability bottleneck of feature detectors, and use transformers to extract position-dependent feature representations. So this is an overview of Lofter. So without a feature detector, Lofter extracts dense matches at a coarse level first and refines the good matches to a subpixel level later on. So this means that each area in the image pair can be potentially matched, and thus the repeatability bottleneck is avoided. And the fine level matching further refines the location of the coarse matches, which will ensure a accurate post estimation. And Lofter has 4 modules, and let's go over each module with some visualizations of the intermediate results. So the first module, the local feature CNN, is just a simple encoder decoder style CNN that extracts 2 levels of local feature maps. And the visualization here is done by PCA. So yeah, the next module is the course level Lofter module, which is the major contribution of our work. So the course level feature maps from the local feature scene are flattened to 1 dimension and combined with the position encoding. And we later use a transformer module, which contains self-interleaved, self and cross attention layers similar to superglue to process and transform the course level local features from multiple types. So intuitively, the self and cross attention layers have global receptive fields that can aggregate relative information from the entire image, either from itself for self attention or from the other image for cross attention. And these attention visualizations demonstrate that the query point in the textured region can look beyond the local surroundings and attend to the regions with rich textures. Together with the position encoding, a position-dependent feature representation can be learned. As shown on the right, the color gradient on the transformed features indicates that the Lofter module can actually transform the local features that are originally closed in their feature space to be distant from each other. This means that the transformed features are not only depending on their local appearances of the input image, but also depending on their positions on the 2 images, which is a position-dependent feature. So after passing through the Lofter module, the course level features are matched with a differentiable matching layer to obtain the course level correspondences. And we refer the watchers to our paper for further details. So finally, a course defined module is used to refine the matches to a subpixel level. 2 patches are first cropped from the higher resolution local features and passed through a smaller Lofter module. So we later use the center. We later use the center feature vector of the left patch to correlate with every pixel on the right patch to get a correlation map, where the final match location can be computed from its expectation of image coordinates. So yeah, and that is the pipeline of Lofter. And then let's see some comparison with some baseline methods. And this is a comparison with the state-of-the-art detector-based feature matching method, superglue. So since there is no interest point detected on the textured regions, superglue can only produce matches on regions with good textures. On the other hand, Lofter produces semi-dense matches that are well distributed in the entire co-visible area, which will help to get a better post estimation. And here's a comparison with the state-of-the-art detector-free method, DRCnet. DRCnet produces matches that have local consensus only, with many incorrect matches, and it produced no matches on purely text-free regions. And for quantitative evaluation, Lofter shows significant improvement compared to both the detector-free baseline DRCnet and the detector-based baseline superglue. In the end, I would like to talk a little bit more about what have we tried to adapt Lofter to IMC. So we basically have done two major attempts, and the first attempt is for the key points. So just like so Lofter always use evenly distributed grid points as key point on the left image, and refines the right match location with both of the images, instead of just like anyone else, basically, for example, like superglue, to extract the key point individually from each images. So this is what we have done in Lofter is acceptable for estimated relative poses between image pair, but it will hinder the performance of SFM, because this will introduce inconsistent key points within a single view, and unrepeatable key points among multiple views. And we have tried to mitigate this problem by pairing Lofter with super point key points on the left image. So the basic idea is that after establishing the course level matches of Lofter, we replace the left grid point with a super point key point if there exists a super point key point in the local window. And the course-defined module in Lofter will also refine the right matches by correlating the interpolated feature vector of the super point key point. And we still keep the grid point. So we still keep the grid, the key point from the regular grids if super point does not produce a key point in a local window. So as you can see in the visualization, the blue points are the regular grid produced by the Lofter course level matches, and the yellow points are from superglue. From super point, and the green cross are the final key points we used in our submission. So yeah, this is the first attempt. So the second attempt we have made is just a greedy matching strategy for feature checks. So this is similar to what Ms. Prune just have mentioned shortly. So this is mainly for adapting the output of superglue to the submission format of IMC. We extract the points with maximum local confidence as the pillar points, and suppress other points with NMS. So the suppressed points within the local window of their corresponding pillar points are merged to the pillar point. And the matches of the suppressed key points are updated accordingly to the pillar points. And however, unfortunately, after we done this, Lofter is not ranked in the top 2 places of IMC with unlimited key points. And the potential reason is that obviously this track merging operation could introduce too much localization error on the feature checks, and thus it could hinder the post accuracy. On the other hand, interestingly, Lofter can still produce more registered matches on some hard cases on the GoogleUrban dataset, where the best entry for unlimited key points cannot register. And yes, similar results also appeared on this Zuich scene. So these results indicates that Lofter potentially has a better matching capability than other methods, but overall posts computed from Lofter are still worse due to the inaccuracies introduced by the greedy track merging. So I think it would be interesting to derive some kind of a new pipeline that is specifically designed for detector-free methods. I mean, a new SFM pipeline that is specifically designed for detector-free methods. So that's been it. The code is fully open sourced, and more results are presented on our project page, and you are welcome to check them out. And also, I want to thank organizers of this workshop for inviting us, and thanks for this great challenge. Okay.
Thanks. There is one question, which is from Ranian in METU. Sorry, did someone say something? I thought maybe he was on Zoom and wanted to ask it himself.
Okay. Yeah.
Anyway, the question is, what is the reason that you are using a square shape to fuse lofter with superpoint key points instead of another shape, more common shape, such as, for instance, a circle?
You mean you are referring to the shape presented here? So is that correct?
I'm guessing.
The square shape. So this is just the local patches in Lofter. So in Lofter we use regular grids. So there's naturally a local window shaped as a square region instead of something like a circular one. So we just naturally adapt the grid the grid local window we used in Lofter. I'm not sure if that is the answer to the question.
I think if not, you can follow up offline. There is another question, which is if there is no depth map to do the supervision, what else do you think can be used as an alternative form of supervision? And how do you think that will affect performance?
Yeah, actually, that's a great question because we actually have tried to use a work called CAPS, which is published in ECCV 2020. And the general idea of CAPS is just to use camera poses as the only source of supervision, and they compute a equipolar loss instead of using dense correspondences and just supervise the correspondences. And we think that it's a possible way to supervise Lofter without the dense correspondences. Yeah, maybe that's a good question.
I think it's definitely doable. Personal plug, we tried that with this and it works surprisingly well. So you may not need very accurate depth. Maybe using just the people constraints is enough to actually solve this. There's no more questions. Please feel free to reach to Jaming if anything else comes up. I wanted to take a second to thank you for showing up because I think you are in China and it's extremely late. So thank you for that. The commitment, we appreciate it. And also for all of the efforts that you made in order to participate in the challenge, which is not very friendly to this type of new methods, such as yours or Trulls or the one that we'll see next. So let's take that as a jump to the next talk, which is from Wei Jiang. Wei.
Great. I mean, I'm having trouble stop sharing. Maybe Wei can just override my share.
Yeah, I think Wei can override you.
Yeah.
Now it works. Good.
Okay, great.
Hello, everyone. I'm Wei Jiang, a PhD. Can you hear me? Okay. I'm a PhD student from the University of British Columbia under the supervision of Professor Kwang. Today, I'll talk about our recent work quarter, correspondence transformer for matching across images. Image correspondence is a fundamental problem in computer vision. It basically tries to answer the question, where does a point go to in the other image? We present quarter, which precisely answers the previous question. Given an image pair and a query coordinate, it predicts the corresponding coordinate value in the other image. Quarter can solve multiple sparse motion, including camera motion as shown in red, multi-object motion as shown in blue, and object pose change as shown in green. To solve the dense correspondences, we can simply feed all pixel location of the image as known as the mesh grid to quarter. Then we can obtain the dense correspondence between the image pair. And we can use the dense correspondence map to warp the right image on top of the latter image as shown here. The quarter network architecture is simple. It has two major components, a CN backbone and a transformer. First, we feed the image pair into the ResNet to obtain the deep feature. Then we stitch the two feature maps together side by side and add the 2D positional encoding to the feature map. Then we feed the feature map to the transformer encoder and let the transformer to relate all the features spatially to solve the ambiguity caused by self-similarity. After that, we feed the output from the encoder together with the query points to the transformer decoder. This step will translate the query points into the space of the other image. Finally, a multi-layer perceptron is used to bring the high-dimensional coordinates to the XY representation. Notice that the input to a ResNet is always 256 by 256, and it limits the spatial accuracy we can get. To obtain highly accurate correspondences, we introduce a zoom-in strategy at inference time. The idea is that we can crop a smaller patch around the prediction and solve the correspondence problem again with quarter given an image pair looks at the zoom-in area. By doing so, we can process high-resolution image in a hierarchical way, also filter out correspondences that are not reliable. We analyzed the effectiveness of zoom-in strategy and find it significantly improved the spatial accuracy. The right curve shows the error histogram when the network always sees the whole image get resized to 256 by 256. And the pink curve shows the error histogram when we zoom in 10 times, which means the network can see a very small patch of the original image with enough resolution. As the curve shown, when we zoom into the image, the error distribution shifts to the left and gets squeezed, yielding more accurate estimates. We also introduce two inference time filtering strategy to filter out unreliable correspondences. First, we filter out points that are drifted during zoom-in. It means the network thinks the previous course solution is wrong. Second, we filter out points that do not form a cycle. The prediction should be cycle consistent, which means if we feed the prediction back to the network, it should give the query points again. If the points doesn't satisfy the cycle consistency, we also reject it. Time to talk about the training. One problem we faced is the training data. Traditional optical flow datasets like Kitty doesn't have enough variance in terms of perspective change and illumination change. The best dataset we can find is MegaDepth dataset. It provides hundreds of scenes with dense depth maps and at consistent scale. It enables us to create a dense correspondence map between an image pair by projecting the depth from one image to another. Once we have the training data, the training is very straightforward. We use two loss terms. The first one is the correspondence loss, which enforces the prediction to be correct. Another loss is the cycle consistency loss, which enforces the prediction to form a cycle with a query. To participate image matching challenge, we use disk as our key points and match them with quarter. And we only keep the matches with mutual agreement. Here we show some results with 2K disk key points. Quarter can predict the correct correspondences even with large scale and perspective changes. Here are some qualitative dense correspondence results on Kitty. Left is one of the input image. The middle one is the predicted dense flow, and the right is the error map. Notice that we've never trained quarter with Kitty, and we've never have ground truth correspondences for the moving objects in MegaDepth datasets. However, quarter generalized quite well to driving scenario. It built correspondences for the moving cars even when the two cars meet each other. And here I will show some demos we made. First one is a plane tracking demo. We try to track the four corners of the paint and overlay another virtual paint on top of it. The second one is two-view reconstruction demo. And here we know the intrinsic and extrinsic of the two images, and we build correspondences between them. And then we can triangulate the dense point cloud out of it. The next demo is facial landmarks tracking. We detect the facial landmarks for the first frame and track them for the following frames. And we also have a very fancy demo on transformer. We call it transformer, correspondent transformer on transformers. To conclude, COTR is a correspondent. To conclude that first, sparse and dense correspondence problem can be formulated into a single framework. Second, we only train COTR once and can apply it everywhere. The third is that depth data can be used for explicit correspondence supervision. Thank you for your time. And they are my amazing collaborators, Eduard, Yan, Andrea, and Kwang. And our code is also online. Thank you.
That's right. I believe we don't have any questions, so let's just jump to the next two talks, which are the winner talks for the image matching challenge. So I'm excited to see what they say. I think the first one is from METU, and it will be Zhang presenting. So I see the screen already.
Thank you, Prof. Thank you, Eduard. Hello, everyone. It's my pleasure to be here today and introduce our method toward the image matching challenge. This work was conducted by Magvi 3D team, including Yu, Xinyang, Dehao, Ran, Zheng, Haotian, Xiao, and Mi Xiaopeng. The first thing we did is to analyze the dataset images. We found some corner cases which would be potentially difficult to deal with, such as plane degradation, large angle rotation, and large scale transformation demonstrated by those examples. Here is our challenge pipeline: pre-processing the images by masking, followed by superpoint and or disk, or combine superpoint with disk as feature detector. Next, softmax refinement help to refine the key points position. Descriptors are extracted after that. Finally, matching and filtering after layer matches are done by superglue and digesting respectively. More specifically, for the pre-processing, dynamic objects occur frequently in the PhotoTourism and GoogleUrban datasets, causing unreliable and unrepeatable key point detectors. To overcome this, we segmented the scene and masked out some classes, including person, sky, car, bus, and bicycle, except for the class person, which was segmented by mask RTN trade on Coco. All other classes were removed by PSP trade on ADE20K. In addition, the area mask was eroded to preserve the details of buildings. Where do the object segmentation net work well under most of circumstances? We found they performed poorly when distinguishing the core portrait from humans. Thus, we additionally trained a binary classifier to take person apart from car portraits. As a result, masking improved the stereo MA by 0.01 on the validation set. Now I will hand it over to my colleague Xinyang to talk more about the detector. Thanks.
We tried the similar method as used in the training process of superpoint, the homographic adaptation, to get better key points. Using this method, we can get more useful key points through one picture, and this can help the following process and provide better matching results. And also, we applied an arc softmax function for key points refinement with a radius of 2, soft argmax refinement, and make the key points more accurate. And we applied non-maximum suppression on the key point score map to finally get the key points location. And we found that a larger NMS radius can help and to make the distribution of the key points more uniform, and which is beneficial for the matching accuracy. To test the effect of the methods we mentioned before, we did experiments on the validation set. In the result, we can see that after using the improvements we mentioned before separately, and the score on the validation set of 2K and key points increased to some extent. And now I will hand it over to my colleague Chen Yu.
We analyze some corner cases and find alignment is crucial to that because the local features may undergo dramatic changes when large transformations are encountered. To solve this problem, we utilize the test-type augmentation, TTA. Specifically, we apply scaling, 90-degree rotation, and 45-degree perspective transformation to generate different descriptors and combine all the matches. However, this operation is time-consuming. In order to save time, we only apply TTA to the image pairs with matrix match length less than 100. Compared with our baseline MSS, the second submission, Scale V2, contains 3 scale descriptors, and the last one, orientation. It includes 90-degree rotation and 45-degree perspective transformations. According to the leaderboard, both submissions can improve the performance on most metrics. Next is the turn of my teammate Zhang Dehao.
For part of training, we have 3 ideas. First of all, we try to fine-tune superpoint with superglue in an end-to-end manner on MacDev's dataset, with this competition test set removed. More specifically, we split the original superpoint into 2 networks. The first one was fixed with the official ways to extract the key points from the image, while the other one was fine-tuned to provide descriptions. However, we found this adjustment advanced the model performance slightly. Secondly, we take the advantage of the latest feature disk. We only train the matcher part, while directly use the official ways of disk to extract the features. Due to the CUDA memory limited, we leverage disk to extract 2048 points for each image in the training phase and 8,000 points in the testing phase. The AUC of OFCC could be improved significantly. As this method didn't surpass the previous superpoint superglue method and competition leaderboard, we guess the reason is that, firstly, we didn't have time to fine-tune the parameters of disk. Secondly, disk was not like superpoint, which trained on widespread data size. The generalization ability of disk may not be very good. Finally, we think the pose in the competition evaluation may not be very accurate to estimate that disk performance. Finally, we combined the advantage of the latest feature disk and superpoint. For each image, we use superpoint to extract 2,000 key points and use disk to extract 6,000 key points. In the matching step, we match the same kinds of descriptors and combine 2 kinds of matches together to form the final matches. We can see this combination boosts a lot in the leaderboard. For the outer layer rejection method, we did a lot of experiments and found that dgensec outperformed other methods. So choose the dgensec as a baseline method to find the fundamental matrix, and under certain circumstances, the homography matrix simultaneously. Inspired by ORB SLAM, different transformation matrix should be selected for different things. In the GoogleUrban dataset, for example, many correct matches are on the flat buildings along the street, and many wrong matches are on the ground or on the isolation belt of the road. Suffering from the weak constraint of F matrix, some wrong matches also could pass the filter. The distance to the epipolar line is less than the threshold. Well, if the H matrix is selected, only the correct matrix matches on the street side flat buildings is retained. For the method implementation, we refer to the ORB SLAM, respectively calculating the F matrix and H matrix, as well as their scores, SF and SH, which are related to symmetric transfer error less than the threshold. After obtaining score of F and the score of H, then we select H matrix. If H score divides H score plus F score is greater than 0.55. Otherwise, we select the F matrix. it performed well on the GoogleUrban datasite. For the future works, there are 3 things we think will improve the results. First one, retrain the pipeline with reinforcement learning. Second one, use the better feature extraction method. And third one, find some refined methods, refine the feature points location by some local feature refinement methods. Thanks for your listening.
Okay, thank you so much for the presentations. I see that a few questions have been asked and already answered in chat. So we'll move on to the final speaker of the challenge participant talks. And unfortunately, it's become too late in China. So we'll play a recording that they've sent us. I hope I do this properly, because I don't want to mess up somebody's hard effort. Okay. And I will also stop sharing my video.
We are glad to give an introduction to our method at the CVPR 2021 Image Matching Workshop. Our method achieves the best performance in the restricted key points category, and we will illustrate our method in 3 parts. First, we will introduce our pipeline. We use pre-trained superpoint during key point detection stage and fine-tuned superglue during key point matching stage. Specifically, we distorted the image with random homography adaptation to improve the repeatability of key points. Then, we use instance segmentation and semantic segmentation to remove useless area. Finally, the origin and the distorted images are fed into the superpoint model to extract key points and corresponding descriptors. To adapt the submission format, we use an autoencoder model to encode the feature dimension from 256 dimension to 128 dimension. During the matching period, the decoded descriptors are fed into the fine-tuned superglue to obtain the matched pairs. Finally, dgensenk is used to reject the outlier matches. For the training of superglue, we use Oxford and Paris dataset to train a basic model with homographies and photometric distortions. Then, we use mega depths without test set on PhotoTourism to fine-tune the basic model. We decrease the bin score during inference, which aims to balance the precision and the matching score. And the training settings are displayed in this page, and the final results shows that our setting achieves comparable performance with the official model on the same test pair set. To adapt the official submission format, we also train an autoencoder model to compress the descriptor. The MSE loss is used to constrain the input descriptor and the decoded descriptor. The final submitted descriptors are encoded to 128 dimension, and the decoded descriptor is used as the input of superglue. The experimental results show that the decoded descriptors achieve similar performance on the validation dataset. In this section, we will introduce the feature adaptation model. First, we perform 49 random adaptations to the original image. Then we fuse the features of the adaptations with 1/10th weight and the original descriptors together by summation. Finally, we fine-tune the superglue model with the fused features. To verify the effectiveness of our method, we choose 3 validation schemes randomly and compare the similarity distribution between average fusion and the proposed fusion. Specifically, we collect the ground truth matching pairs and evaluate the distribution of cosine similarity distance. Then, we calculate the distribution difference between average fusion and the proposed fusion. The experimental results show our method obtain more pairs than average fusion on the high similarity section, and less pairs on the low similarity section. Finally, we will share some effective tricks during the computation. First, we split 4 backgrounds with semantic segmentation and instance segmentation. We mask including person, sky, car, bus, train, chalk, and advertising board during key point extraction stage. All segmentation results are generated from open source algorithm, which is shown below. Moreover, for some schemes with status, we ignore the labels of person to avoid the misclassification. Besides, we try different thresholds of DE-Gen-Senk and evaluate the AUC at 10 degrees to find a suitable threshold to evaluate for each scheme. At last, we use 1 for PhotoTourism, 2 for PragueParks, and 1.2 for GoogleUrban. This table shows the results of different versions in validation and leaderboard. The green one achieves the best performance in this computation. Finally, we want to share an interesting result with 2-stage adaptation. For image pairs with few matches, we adopt 2-stage matching progress. We split each image into 9 half-size patches and extract matches between the patches and the full image. The matches are filtered by the sharing point set between patch to full. The pair with the most matches is selected as the final result. The visual result shows that our proposed 2-stage can increase the matches significantly, and we will verify the effectiveness on the test set later on. Thank you.
Okay, that was the last presentation, one of the winners of the challenge. To the winners of both the image matching challenge and the SimLocMatch challenge, we'll email you in a few days about how to figure out the shipping of the price. It would be nice if next year we can finally do this in person and simplify things a little bit, but that's where we are. And thank everyone for attending. It's been relatively smooth with a few technical complications, but I think we've been able to highlight a number of works. We skipped one of the sessions that I would like to have had this time, but if you have any questions, any suggestions on how to improve the challenge, even silly things like is it difficult to submit, are your uploads failing for some reason, please let us know. If you are working on papers that you think we don't accommodate enough, such as some of the examples that we saw today, please just reach out to us and we'll try to see what we can do about it. But yeah, I'd like to thank all of the speakers. I think we've had some very nice talks today, and hope we can renew this next year. As you know, workshops at the level of CVPR are getting more and more competitive, but we have been able to have it 3 times in a row, for which I'm quite happy. And hopefully we can do this again next year in person. Thanks, everyone. See you next year. I think we can stop the recording.
I'm trying to figure out